The observable universe extends 93 billion light-years in diameter, 46.5 billion light-years in every direction from Earth, encompassing everything from which light could have reached us during the 13.8 billion years since the Big Bang. This boundary represents the particle horizon, defining the limit of causally connected space beyond which information cannot reach us given finite age and finite light speed. The counterintuitive fact that the observable radius exceeds the universe's age times light speed, which would yield only 13.8 billion light-years, results from cosmic expansion stretching space itself during photons' journeys toward Earth. A photon emitted from the edge of the observable universe shortly after the Big Bang traveled through expanding space, with the emission point receding continuously as expansion carried it farther away. In today's coordinates, accounting for this expansion, that emission point lies 46.5 billion light-years distant, despite light taking only 13.8 billion years to traverse the journey. This represents our cosmic horizon and observational boundary, not a physical edge beyond which lies more universe, possibly infinite, forever hidden from view. The particle horizon encompasses the maximum extent of space with which we share causal contact regions from which signals could have reached us and vice versa. This differs fundamentally from physical edges or boundaries. Space doesn't end at the particle horizon. It continues beyond, containing galaxies, stars, and structures we can never observe because their light hasn't had time to reach us. The horizon grows over time as light from increasingly distant regions arrives, bringing previously invisible structures into view. In a static universe, the particle horizon would equal the universe's age times light speed. But cosmic expansion, particularly the early rapid expansion during radiation domination and the current accelerating expansion driven by dark energy, complicates this relationship. The comoving distance in today's coordinates, after accounting for expansion to the particle horizon, is calculated by integrating the speed of light divided by the scale factor from the Big Bang to present, yielding 46.5 billion light-years. The cosmic microwave background surface represents the most distant structure we can observe electromagnetically, located at co-moving distance 46.1 billion light-years just inside the particle horizon. This surface, emitted 380,000 years after the Big Bang at redshift Z, approximately 1100, marks the epoch of recombination when neutral hydrogen formed and photons decoupled from matter, streaming freely through space ever since. We observe the CMB as a nearly uniform glow at microwave wavelengths, with temperature 2.725 Kelvin, cooled from 3000 Kelvin at emission by cosmic expansion, redshifting photons by factor 1100. The look-back time to the CMB is 13.8 billion years, meaning we see it as it appeared when the universe was 380,000 years old, roughly 0.003% its current age. Observations cannot penetrate beyond the CMB surface using electromagnetic radiation because earlier epochs were opaque photons constantly scattered off free electrons in ionized plasma, preventing propagation. The CMB thus represents our ultimate electromagnetic horizon, the oldest light observable. The Hubble sphere, with radius approximately 14 billion light-years, defines the distance where cosmic expansion causes recession velocity to equal light speed. Objects beyond the Hubble sphere recede faster than light due to space itself expanding, not violating relativity, since nothing moves through space faster than light, but space can expand at any rate. The Hubble radius equals c divided by the Hubble parameter h0, currently 67.4 kilometers per second per megaparsec, according to Planck satellite measurements. Converting units yields roughly 14 billion light-years. Objects currently beyond this distance are receding superluminally their recession velocity from expansion exceeds light speed. Yet, we observe many such objects because they were inside the Hubble sphere when they emitted the light we now receive. As space expanded during photons' transit, objects crossed outside the Hubble sphere, while their previously emitted light continued approaching us. Conversely, objects currently inside the Hubble sphere, but near its edge, will eventually cross outside as dark energy accelerates expansion. The event horizon, located at approximately 16 billion light-years co-moving distance, defines the future visibility limit, the boundary beyond which objects recede so fast that light emitted now or in the future will never reach us, regardless of how long we wait. Dark energy's accelerating expansion drives this effect. Objects beyond 16 billion light-years are receding faster than their light can approach us. Photons emitted toward us are swept away by expansion, unable to close the distance. Over trillions of years, the event horizon contracts as acceleration increases, eventually bringing galaxies currently observable but distant across the boundary, causing them to fade from view permanently. In 150 billion years, only the local group and nearby groups within roughly 10 million light-years will remain visible. Everything beyond will have crossed the event horizon and disappeared. This represents a fundamental limit on future observability imposed by dark energy, contrasting with the particle horizon which grows with time in non-accelerating universes. The observable universe contains approximately 2 trillion galaxies based on deep survey extrapolations, accounting for faint galaxies below detection thresholds. Early estimates from Hubble Deep Field suggested 100 billion to 200 billion galaxies, but deeper observations resolving fainter objects increased counts. Each galaxy contains 100 million to 1 trillion stars, depending on type. Dwarfs have millions to billions, while giants have hundreds of billions. Averaging 100 billion stars per galaxy yields 10 to the 23rd stars, 200 billion trillion in the observable universe. The observable universe also contains approximately 10 to the 80th atoms, calculated from average baryon density 0.25 atoms per cubic centimeter times observable volume 4 times 10 to the 80th cubic meters. Most atoms reside in intergalactic gas rather than stars. Dark matter outweighs baryonic matter by factor 5 to 1, contributing 10 to the 81st dark matter particles, if dark matter is particulate, though dark matter's nature remains unknown. The edge of the observable universe is defined by light travel time, not physical boundary. It's an observational limit, not a material surface. Every observer, at every location, sees themselves at the center of their own observable universe, bounded by their particle horizon. An observer in a galaxy 10 billion light-years away sees a different observable universe, overlapping ours partially but extending 46.5 billion light-years in their directions beyond our view. The observable universe is observer-dependent. Analogous to the horizon on Earth, every observer sees a different horizon depending on their location, yet Earth has no edge. Similarly, the universe likely has no edge, extending infinitely beyond our horizon, or wrapping back on itself if spatially closed, though observations indicate flat geometry consistent with infinite extent. The concept of the universe's edge, as observational rather than physical, is crucial. We're not at a privileged location near an edge, but at the center of our local observational sphere, limited by light speed and age. Beyond the particle horizon lie causally disconnected regions from which no signal has reached us, and none will reach us before they cross the event horizon if dark energy persists. These regions are not merely difficult to observe, but fundamentally unobservable given current physics. If the universe is infinite, infinitely many galaxies exist beyond our horizon, forever inaccessible. Even if finite, the unobservable region vastly exceeds the observable estimates, suggests the total universe exceeds the observable by at least factor 250 based on CMB constraints, searching for topological patterns that would appear in small wrapped universes. The unobservable universe's properties remain unknown. It might differ dramatically different physical constants from symmetry breaking, different density fluctuations, different structure, or it might be statistically identical. The cosmological principle extended globally suggests uniformity. We cannot know through direct observation, only through theoretical extrapolation and assumptions about cosmic structure beyond our horizon. The cosmological principle under scrutiny. The cosmological principle, foundational to modern cosmology since Einstein's 1917 static universe model, asserts that the universe appears homogeneous and isotropic when averaged over sufficiently large scales. No preferred locations or directions exist. Homogeneity means matter distributes uniformly with no special places having higher or lower density than elsewhere. Isotropy means the universe looks the same in all directions with no preferred axes. These assumptions simplify Einstein's field equations dramatically, allowing solvable cosmological models like Friedmann-Lemaitre, Robertson-Walker metric, describing expanding homogeneous isotropic universes. The principle is not assumed blindly, but tested observationally. Galaxy surveys, mapping millions of galaxies across billions of light-years, assess whether structure becomes uniform on large scales. The cosmic microwave background's temperature uniformity to 1 part in 100,000 across the sky provides the strongest isotropy evidence. Deviations from the cosmological principle would require fundamentally different theoretical frameworks, potentially invalidating standard cosmology. The homogeneity scale represents the distance beyond which density fluctuations average out, and the universe appears statistically uniform. Below this scale, structure is highly non-uniform galaxies, cluster into groups, clusters, superclusters, and filaments with voids between. Above this scale, these structures average to uniform density. Theoretical predictions from inflation and lambda CDM suggest homogeneity emerges around 300 to 400 million light-years. Observations from galaxy surveys broadly confirm this correlation functions, measuring how galaxy clustering depends on separation drop to near zero beyond 300 to 500 million light-years, indicating statistical uniformity. However, individual structures like the Sloan Great Wall at 1.37 billion light-years and potentially larger structures challenge this picture, raising questions whether homogeneity truly emerges at predicted scales or whether rare, large fluctuations occur more frequently than lambda CDM predicts. CMB temperature measurements show remarkable uniformity, 2.7255 Kelvin everywhere on the sky to within 18 microkelvin root mean square after removing the dipole from our motion. This 1 part in 100,000 uniformity indicates conditions at recombination were extraordinarily smooth across causally disconnected regions spanning the entire observable universe. The COBE satellite first detected these tiny fluctuations in 1992. WMAP and Planck satellites mapped them with exquisite precision, revealing acoustic oscillation sound waves in the photon baryon plasma imprinted as hot and cold spots at characteristic angular scales. These fluctuations match predictions from simple power law primordial fluctuations generated during inflation, supporting both inflation and the cosmological principle. However, subtle anomalies, including the cold spot, axis of evil alignment, and hemispherical asymmetry, suggest deviations from perfect statistical isotropy, challenging whether the cosmological principle holds absolutely. Large-scale structure surveys including the Sloan Digital Sky Survey mapping 930,000 galaxy spectra across 10,000 square degrees, the 2-degree Field Galaxy Redshift Survey with 220,000 galaxies, and the Baryon Oscillation Spectroscopic Survey extending SDSS with 1.5 million galaxy redshifts have created three-dimensional maps of cosmic structure across billions of light years. These surveys reveal the cosmic web filaments, walls, nodes, and voids organizing galaxies hierarchically. Statistical analyses measuring power spectra, correlation functions, and topology test whether structure matches lambda CDM predictions. Generally, agreement is excellent on scales 10 to 300 megaparsecs, but discrepancies appear. Structures like the Sloan Great Wall exceed expected maximum sizes. Void sizes and abundances show tensions with simulations, and the distribution's overall smoothness, parameterized by SATE, measuring matter clumping amplitude, shows mild tension between different measurement methods. Statistical isotropy tests analyze whether the universe's properties depend on direction. The CMB provides the cleanest test if isotropic fluctuation statistics should be identical in all sky directions. The cosmological principle predicts that the quadrupole moment's orientation should be random relative to the octopole's orientation, that power should be equal in all directions, and that no preferred axes exist. Observations violate these expectations. The CMB's lowest multipoles align with each other, and with the ecliptic plane, the axis of evil. Additionally, one hemisphere shows 7% higher fluctuation power than the opposite hemisphere, the hemispherical asymmetry. These anomalies have low but not vanishingly small probability under isotropy assumptions. Interpretations range from statistical flukes due to cosmic variance at low multipoles, to systematic foreground contamination, to genuine cosmological signals indicating pre-inflationary physics or space beyond our horizon affecting observable conditions. Violations of the cosmological principle include the CMB cold spot, a 10-degree region, 70 microkelvin, colder than average, with probability less than 1 inch 1000 for random Gaussian fluctuations. The axis of evil alignment of low multipoles with ecliptic plane has probability less than 1%. Hemispherical asymmetry, showing 7% power difference between hemispheres, is statistically significant at 3 to 4 sigma. The Sloan Great Wall at 1.37 billion light-years, and Hercules Corona Borealis Great Wall, potentially 10 billion light-years, challenge the 300 to 400 million light-year homogeneity scale. Dark flow coherent bulk motions of galaxy clusters to 1,000 kilometers per second in specific directions, if confirmed, would indicate massive structures beyond the observable universe influencing our local region. These anomalies individually have marginal statistical significance, but collectively suggest either systematic issues with observations, cosmic variance producing rare fluctuations within standard model, or genuine new physics beyond lambda CDM. The Sloan Great Wall's 1.37 billion light-year extent challenges lambda CDM cosmology, because structures exceeding 1 billion light-years approach the cosmological homogeneity scale and require formation times approaching the universe's age. Growing such structures from 1 part in 100,000 initial fluctuations visible in the CMB requires billions of years of gravitational amplification. Simulations using lambda CDM show billion light-year structures can form as rare high sigma fluctuations, several standard deviations above average density, but should be exceedingly rare. The Sloan Great Wall's existence marginally fits predictions, occurring in roughly 1% of simulated volumes. If additional comparably sized structures exist, or If the Hercules Corona Borealis Great Wall's 10 billion light-year length is confirmed, lambda CDM would face serious challenges. Current data suggests these structures lie at lambda CDM's edge of plausibility, not impossible but uncomfortable, raising questions whether the cosmological principle fails on the largest scales. Tensions between observations and lambda CDM predictions manifest in several areas beyond large structures. The Hubble constant H0 shows 5 sigma discrepancy between early universe measurements from CMB and late universe measurements from supernovae and Cepheids. The SATE parameter, measuring matter clumping, shows 2 to 3 sigma tension between CMB, weak lensing, and cluster counts. The lensing amplitude from Planck CMB lensing is lower than expected by 2 to 3 sigma. These tensions could indicate systematic measurement errors or could signal breakdowns in lambda CDM assumptions. Perhaps dark energy evolves rather than being constant. Perhaps general relativity needs modification on cosmological scales. Perhaps neutrinos have higher masses than assumed. The cosmological principle itself might fail if we live in an atypical region, a large void or overdensity. Local measurements would systematically differ from global averages inferred from CMB. Resolving these tensions represents cosmology's central challenge. Anomalous galaxy velocities, dark flow. Dark flow refers to a claimed large-scale coherent bulk motion of galaxy clusters at velocities 600 to 1000 km per second toward a specific direction in the constellation Centaurus and Hydra, discovered by Alexander Kashlinsky and colleagues in 2008 using data from the Wilkinson Microwave Anisotropy Probe satellite. The discovery analyzed the kinematic Sunyaev-Zeldovich effect, the Doppler shift of cosmic microwave background photons, scattering off hot electrons in galaxy cluster gas. Clusters moving toward Earth produce slight CMB temperature increases through blue-shifted photons, while clusters moving away produce decreases through red-shifted photons. By measuring CMB temperature deviations at hundreds of X-ray identified cluster positions and stacking signals statistically, Kashlinsky's team claimed detection of coherent motion far exceeding lambda CDM predictions for random, peculiar velocities at these distances. The flow direction points roughly toward the Shapley supercluster, but appears to extend beyond it, suggesting influence from structures outside the observable universe or from pre-inflationary fluctuations, creating large-scale superhorizon modes. The discovery paper, published in 2008, analyzed 700 X-ray selected galaxy clusters within redshift Z less than 0, 3 corresponding to distances up to 3 billion light-years. Measuring each cluster's peculiar velocity individually through kinematic SZ is impossible due to noise, but statistical stacking of hundreds of clusters revealed a net dipole pattern clusters in one hemisphere, systematically moving one direction, while clusters in opposite hemisphere move the opposite direction, indicating bulk flow. The measured velocity was 600 plus or minus 150 kilometers per second, significantly exceeding the roughly 200 kilometers per second expected from lambda CDM structure within the observable universe. Subsequent analyses, extending to higher redshifts and larger cluster samples, claimed the flow persists to Z approximately 0.3 and possibly beyond, affecting thousands of galaxy clusters across gigaparsec scales. If confirmed, this would constitute severe tension with lambda CDM, which predicts bulk flows should decrease with distance and average to 0 beyond several hundred million light-years, as random motions from local structure cancel out. The dark flow direction points toward constellation Centaurus and Hydra at galactic coordinates roughly L equals 280 degrees, B equals 0 degrees, within 20 degrees of the direction toward Shapley supercluster at 600 and 50 million light-years. Initially, this suggested Shapley's enormous mass, 10 to the 16th solar masses or more, might explain the flow through gravitational attraction. However, simulations show Shapley alone cannot produce 600 km per second velocities at 3 billion light-year distances. Either the flow direction coincidentally aligns with Shapley while being caused by more distant structures, or Shapley is merely the nearest component of a much larger mass concentration extending beyond the observable horizon. The latter scenario invokes matter beyond the particle horizon, gravitationally affecting our local region, allowed if superhorizon density fluctuations existed before inflation stretched them beyond causal contact, or if our observable universe is merely a finite patch of infinite space with large-scale gradients. The magnitude of 600 to 1000 km per second vastly exceeds lambda CDM expectations for bulk flows at gigaparsec scales. Standard structure formation predicts bulk flows from gravitational attraction of overdense regions and repulsion from voids within the observable universe. These flows decrease with distance as more structure is included in averages, cancelling positive and negative contributions. At 300 megaparsecs, lambda CDM predicts bulk flows around 150 to 200 km per second. At 1 gigaparsec, predictions drop to 50 to 100 km per second. Observed dark flow of 600 to 1000 km per second at 1 gigaparsec thus exceeds predictions by factor 10. This huge discrepancy suggests either the observations are wrong, systematic errors mimicking dark flow, or lambda CDM is incomplete, missing physics that generates large-scale motions. Possible explanations include massive structures beyond the observable universe, non-Gaussian primordial fluctuations creating rare extreme structures, anisotropic expansion from pre-inflationary conditions, or modified gravity theories producing enhanced large-scale flows. Possible causes of dark flow, if real, include massive structures beyond the observable universe exerting gravitational pull on our local region. If the universe extends infinitely or far beyond our 3 billion light-year observable diameter, large-scale density gradients could exist with massive superclusters beyond our horizon pulling matter coherently. Pre-inflation fluctuations representing primordial inhomogeneities existing before inflation stretched to superhorizon scales, but still influencing our observable patch, could create preferred directions and bulk flows. Anisotropic expansion, where space expands faster in some directions than others, violating isotropy assumptions, would produce apparent bulk flows as distance redshift relations vary with direction. Topological defects like cosmic strings or domain walls from early universe phase transitions could create large-scale velocity patterns. Modified gravity theories altering gravitational dynamics on cosmological scales might enhance structure and flows beyond general relativity predictions. Each explanation has theoretical challenges and requires verifying the dark flow observation first. Controversy surrounds dark flow claims, with several independent studies finding no significant detection. Planck satellite collaboration analyzed kinematic SZ using their higher resolution CMB maps and larger cluster samples, finding marginal evidence at best bulk flow velocities consistent with zero within uncertainties, or at most 150 to 250 km per second, compatible with lambda CDM predictions. Other groups, using different cluster catalogs, different CMB maps, and different analysis techniques, also report non-detections or much weaker signals than Kashlinsky's team. The discrepancies might arise from different cluster selection criteria, different methods for estimating cluster velocities, foreground contamination from galactic emission, or instrumental systematics. Kashlinski's team argues their methods are robust, and critics misapply techniques, while critics contend the original detection resulted from unaccounted systematics or statistical flukes. The debate remains unresolved, with consensus leaning towards skepticism absent confirmation from independent methods. Planck satellite data, analyzed by multiple groups, yielded inconclusive results regarding dark flow. Some analyses found marginal evidence for bulk flow velocities 200 to 300 km per second, consistent with lambda CDM, or slightly enhanced but far below the 600 to 1000 km per second claimed originally. Other Planck analyses found results consistent with zero bulk flow within uncertainties. The Planck collaboration's official papers discussing kinematic SZ and bulk flows concluded that current data do not require dark flow to explain observations. Lambda CDM predictions adequately fit the data. However, data also don't definitively rule out modest bulk flows 200 to 300 km per second. Definitive resolution requires future surveys with larger cluster samples, better CMB maps, and independent methods like spectroscopic peculiar velocity surveys measuring galaxy redshifts and distances directly. Until consensus emerges from independent observations, dark flow remains a tantalizing hint of possible new physics, but far from confirmed. The CMB cold spot supervoid. The CMB cold spot supervoid. The CMB cold spot, a roughly 10-degree diameter region in the constellation Eridanus, appearing 70 microkelvin colder than the average 2.725 Kelvin cosmic microwave background temperature, represents one of the most significant anomalies in cosmological observations. Discovered in 2004 WMAP data and confirmed with higher significance by Planck satellite observations in 2013, this feature spans approximately 20 moon diameters on the sky, far larger than typical CMB fluctuations, which measure arc minutes to few degrees. The cold spot's 70 microkelvin temperature deficit, while tiny in absolute terms, is enormous relative to typical 18 microkelvin root mean square fluctuations after removing the dipole anisotropy from Earth's motion. Statistical analyses indicate probability less than 1 inch 1,000 that such a large cold region would appear randomly in Gaussian fluctuations predicted by standard inflation models. This low probability has sparked intense investigation into whether the cold spot represents a statistical fluke, observational artifact, signature of exotic physics, or evidence for structures beyond the observable universe. The cold spot's location in constellation Eridanus at celestial coordinates approximately right ascension 3 hours 15 minutes, declination -19 degrees, places it in the southern hemisphere, sky visible from southern latitudes year-round and from northern mid-latitudes during winter months. The feature shows elongated morphology rather than circular symmetry, extending roughly 10 degrees in its long axis and 5 degrees across, though defining exact boundaries is subjective, since temperature transitions gradually rather than abruptly. Multiple independent analyses using different statistical methods, Gaussianity tests, wavelet decompositions, matched filters, consistently identify this region as the coldest large-scale feature in the CMB. The feature's temperature reaches minimum 70 microkelvin below average at its center, with deficit declining gradually toward edges over several degrees. Smaller scale hot and cold spots appear throughout the CMB from acoustic oscillations, but none approaches the cold spot's combination of size and amplitude. Discovery occurred when researchers analyzing WMAP first-year data in 2004 noticed an anomalously large cold region. Initial reaction was skepticism, perhaps a foreground contamination from galactic emission, instrumental artifact, or statistical fluctuation. Subsequent data releases from WMAP and eventually Planck satellite with superior sensitivity and resolution, confirmed the feature's reality and cosmic origin rather than foreground or instrumental. Foreground subtraction removes galactic dust emission, synchrotron radiation, and free emission that could mimic cold spots, but the anomaly persists. Null tests comparing different frequency channels, different sky coverage, and different detectors find consistent results, ruling out instrumental systematics. The cold spot is real, cosmic, and primordial, originating from conditions at recombination 380,000 years after the Big Bang. The question is whether it represents a rare but allowed fluctuation within standard inflation, or indicates new physics. The Eridanus supervoid provides a potential physical explanation for the cold spot through the integrated Sachs-Wolf effect. Discovered in 2015 through galaxy surveys mapping the region's three-dimensional structure, this void extends approximately 1.8 billion light-years in diameter, centered at redshift Z approximately 0.22, corresponding to distance roughly 2.5 billion light-years. Galaxy number counts show 20 to 30% underdensity compared to cosmic average significantly depleted but not completely empty. Voids of this scale are rare but not unprecedented in lambda CDM cosmology. The void's size, location aligning with the cold spot, and timing photons from the CMB passed through this region roughly 6 to 7 billion years ago, when the void was forming, suggest causal connection. The integrated Sachs-Wolf effect predicts CMB photons crossing large voids experience net redshift, appearing colder because they lose energy climbing out of gravitational potentials that weakened during transit due to dark energy accelerating void expansion. The ISW effect operates through time-varying gravitational potentials caused by dark energy's influence on structure growth. When CMB photons enter an underdense void, they blue shift slightly, gaining energy falling into the shallow potential well. Upon exiting, they redshift, losing energy climbing out. In a static universe, these shifts cancel perfectly. Energy gained entering equals energy lost exiting. However, dark energy causes voids to expand and deepen over time. Photons exit through a shallower potential than they entered because dark energy stretched the void during transit, making the exit potential less negative. The exit redshift therefore fails to fully cancel the entrance blue shift, resulting in net energy loss. Photons emerge redder and cooler. For typical voids 100 to 300 million light-years across, ISW produces temperature changes a few microkelvin. Larger supervoids produce proportionally larger effects. The Eridanus supervoid's 1.8 billion light-year size should generate ISW temperature deficit 10 to 20 microkelvin, according to standard calculations. The predicted ISW effect of 10 to 20 microkelvin falls far short of the observed 70 microkelvin cold spot, creating a factor 3.5 discrepancy between prediction and observation. This discrepancy is the core mystery. Either the void explanation is incomplete, requiring additional voids aligned along the line of sight or non-standard void properties, or the cold spot has a different origin entirely. Some studies propose multiple smaller voids along the same sightline collectively producing the observed deficit, though finding such an alignment seems contrived. Others suggest the void is colder or denser than standard assumptions, enhancing ISW. Alternative explanations invoke non-Gaussian primordial fluctuations, inflation models predicting occasional rare, large amplitude fluctuations exceeding Gaussian predictions, or exotic physics, including cosmic texture defects from symmetry-breaking phase transitions, or even multiverse collisions, imprinting circular cold spots. None of these alternatives has achieved consensus, leaving the cold spot's origin debated. Alternative theories explaining the cold spot without invoking supervoids include cosmic textures, topological defects, formed during symmetry-breaking phase transitions in the early universe, predicted by some grand unified theories. Textures are localized field configurations that form, evolve, and decay, releasing energy and creating gravitational effects, including temperature perturbations in the CMB. Unlike domain walls, strings, and monopoles, which are stable defects, textures are unstable and decay over cosmological timescales. The decay imprints characteristic signatures on the CMB, including localized cold spots surrounded by hot rings. Some analyses suggest the cold spot's morphology matches texture predictions, though detailed statistical tests find marginal agreement at best. Texture models face challenges from Planck constraints limiting defect contributions to CMB power spectrum to less than a few percent, making large individual features like the cold spot difficult to explain. The multiverse collision hypothesis, proposed by Laura Mersini-Houghton and colleagues, suggests the cold spot results from our bubble universe colliding with a neighboring bubble universe during eternal inflation. In eternal inflation scenarios, inflation continues eternally in most regions, while ending in finite bubbles like ours, where symmetry breaking allows particle physics and structure formation. These bubbles expand and occasionally collide, with collisions imprinting circular temperature patterns on the CMB cold spots at collision centers surrounded by hot rings where energy concentrates. Mersini-Houghton's team predicted this signature before WMAP data and claimed the cold spot confirms their prediction. However, detailed searches for circular temperature patterns in Planck data found no convincing collision signatures matching theoretical predictions. Most cosmologists remain skeptical, viewing the multiverse collision hypothesis as highly speculative without independent evidence for eternal inflation or bubble nucleation. The cold spot might coincidentally resemble collision predictions without being actual collision evidence, the axis of evil and hemispherical asymmetry. The axis of evil refers to the unexpected alignment of the cosmic microwave background's lowest multipole moments, the quadrupole and octopole with each other, and with the ecliptic plane defining Earth's orbital plane around the Sun, and the equinoxes marking seasonal transitions. Discovered in WMAP data and confirmed by Planck, this alignment has probability less than 1% under the assumption that CMB fluctuations are statistically isotropic with randomly oriented multipoles. The term axis of evil, coined by physicist João Magajo, captures the feature's unsettling implications. Either the alignment is a statistical fluke with low but non-zero probability, or it indicates systematic contamination from solar system or galactic foregrounds. Or most disturbingly, it reveals genuine preferred directions in the universe, violating the cosmological principle's isotropy assumption. The alignment points roughly toward the ecliptic plane and equinox direction, raising suspicions of foreground contamination, though extensive analysis has failed to identify plausible contaminants. The quadrupole moment, designated L equals 2 inches spherical harmonic decomposition of CMB temperature fluctuations, represents the largest scale pattern after the dipole from Earth's motion. The quadrupole divides the sky into 4 regions, 2 hot and 2 cold, arranged symmetrically. In statistically isotropic fluctuations, the quadrupole's orientation should be random. Similarly, the octopole, with L equals 3, divides the sky into 8 regions with random orientation. WMAP and Planck data show these 2 multipoles align with each other, their hot and cold regions coincide spatially despite being independent random fields, according to inflation theory. Additionally, both align with the ecliptic plane within 5 to 10 degrees. The probability of such alignments occurring randomly is calculated through Monte Carlo simulations, generating millions of random CMB realizations and counting how often similar alignments appear by chance. Results indicate probability 1 to 2% low, but not impossible. The alignment with the ecliptic plane and equinox direction immediately raises foreground contamination concerns. The ecliptic plane marks the solar system's orbital plane, where zodiacal light from dust-scattering sunlight concentrates. The equinoxes mark directions toward the sun at spring and autumn equinoxes, potentially related to seasonal variations in satellite observing condition. However, extensive foreground analysis, including zodiacal emission modeling, interplanetary dust mapping, and systematic error studies, finds no plausible contaminant producing the observed multipole alignment. Zodiacal emission is orders of magnitude too weak and has wrong spectral signature. Seasonal systematic errors would affect all multipoles similarly, not selectively the lowest ones. Galactic foregrounds concentrated near the galactic plane, not the ecliptic. After accounting for all known foregrounds and systematics, the alignment persists, suggesting either unknown systematic errors or genuine cosmological signal. The probability of less than 1% for random alignment means this feature represents a 2 to 3 sigma anomaly, statistically significant, but not overwhelmingly so. In statistical analysis, 5 sigma significance probability, less than 1 inch 3.5 million, is generally required for claiming discovery. The axis of evil falls well short of this threshold. Additionally, the look elsewhere effect applies when searching data for any unusual pattern without pre-specifying what pattern to expect. The effective probability increases because many possible patterns could have been noticed if present. The axis of evil was discovered through data exploration rather than predicted beforehand, so its true statistical significance is likely less than the nominal, less than 1%. Nevertheless, the feature remains intriguing because it represents one of several CMB anomalies: cold spot, hemispherical asymmetry, lack of large angle correlations that collectively suggest possible deviations from the simplest inflation prediction. Hemispherical asymmetry refers to the observation that one hemisphere of the CMB sky shows approximately 7% higher fluctuation power than the opposite hemisphere, violating statistical isotropy, which predicts equal power in all directions. Discovered in WMAP data and confirmed with higher significance by Planck, this asymmetry manifests as a dipole modulation. The fluctuation amplitude varies sinusoidally across the sky, with maximum in one direction and minimum in the opposite direction. The preferred axis defining the high-power hemisphere points roughly toward galactic coordinates L, approximately 220 degrees, B, approximately minus 20 degrees, within 30 degrees of the direction toward Virgo cluster. Multiple independent analyses using different methods, pixel domain analysis, harmonic domain analysis, wavelet decomposition, consistently detect this asymmetry at 3 to 4 sigma significance. The asymmetry appears primarily at large angular scales, multipoles L less than 64, weakening at smaller scales. The asymmetry axis points toward galactic coordinates, approximately L equals 220 degrees, B equals minus 20 degrees, corresponding to a direction in the general area of Virgo cluster, but not precisely aligned. This direction also lies within 20 to 30 degrees of the CMB dipole direction from Earth's 370 km per second motion relative to the CMB rest frame. The near alignment between asymmetry axis, dipole direction, and Virgo direction suggests possible physical connection. Perhaps our motion through space or gravitational influence from Virgo affects CMB observations in subtle ways not fully removed by standard analysis. However, detailed studies find no plausible mechanism by which Virgo's gravity or Earth's motion could produce 7% power asymmetry. The alignment might be coincidental. Alternatively, the asymmetry might result from pre-inflationary physics creating genuinely preferred directions in the universe, such as anisotropic expansion during inflation, or superhorizon curvature perturbations, affecting our observable patch. The hemispherical asymmetry was discovered through systematic searches for deviations from statistical isotropy in WMAP data. Researchers divided the sky into hemispheres along all possible axes and measured fluctuation power in each hemisphere, searching for axes showing maximum power difference. The observed 7% difference along the preferred axis emerged from this search, confirmed through thousands of Monte Carlo simulations, testing whether similar asymmetries appear in Gaussian isotropic realizations. Less than 1% of simulations showed comparably strong asymmetries, establishing statistical significance. Planck satellite data, with improved sensitivity, confirmed the asymmetry at higher significance, ruling out instrumental artifacts or foreground contamination specific to WMAP. The asymmetry is real and cosmological. Its origin remains. Debated possibilities include primordial physics during or before inflation, statistical fluke from cosmic variance at low multipoles, or, as yet unidentified, systematic errors in data analysis. Confirmation by Planck satellite eliminated possibility that hemispherical asymmetry resulted from WMAP-specific instrumental effects or analysis choices. Planck, observing with different detectors, different scan strategy, and independent data processing pipeline, measured CMB fluctuations across 9 frequency channels from 30 to 857 GHz. Planck's temperature maps show the same 7% hemispheric power difference along nearly identical preferred axis as WMAP, confirming the feature's reality. Planck's polarization measurements, unavailable from WMAP with comparable sensitivity, also show asymmetry in E-mode polarization power, strengthening cosmological interpretation. If the asymmetry resulted from unremoved foreground contamination, it would not appear consistently across temperature and polarization and would show frequency-dependent signatures matching foreground spectra. Planck data show none of these characteristics, strongly indicating the asymmetry is primordial rather than contamination. Unexpected temperature variations in distant CMB. CMB temperature measurements establish its current value as 2.7255 Kelvin, with uncertainty 0.0006 Kelvin, making it one of the most precisely determined cosmological parameters. This temperature represents the cooled remnant of the 3000 Kelvin thermal radiation from recombination, redshifted by factor 1100 through 13.8 billion years of cosmic expansion. The temperature's uniformity across the sky to 1 part in 100,000 after removing the 3.36 millikelvin dipole from Earth's 370 km per second motion indicates extraordinary thermal equilibrium in the early universe. Inflation theory explains this uniformity by proposing exponential expansion that stretched a causally connected region smaller than an atom to encompass the entire observable universe, allowing thermalization before expansion froze fluctuations. However, precise measurements reveal subtle temperature variations, acoustic oscillations, gravitational effects, foreground contaminations that require careful modeling and analysis to interpret correctly. The Sunyaev-Zeldovich effect, discovered in 1970 by Rashid Sunyaev and Yakov Zeldovich, describes inverse Compton scattering where CMB photons passing through hot ionized gas in galaxy clusters gain energy from collisions with high-energy electrons, shifting photon spectrum toward higher frequencies. This thermal SZ effect creates temperature decrements at frequencies below 217 GHz, the crossover frequency where Rayleigh-Jeans and Wien's spectral regimes transition and temperature increments at higher frequencies. The effect's magnitude depends on gas temperature, typically 10 to 100 million Kelvin in rich clusters, and electron column density along the line of sight. Observations detect SZ signals from thousands of galaxy clusters, using them to measure cluster masses, gas properties, and cosmological parameters. The SZ effect provides distance-independent cluster detection signal strength, depends on cluster mass and temperature, but not distance, making it valuable for finding high redshift clusters invisible to optical surveys. The kinematic Sunyaev-Zeldovich effect, distinct from thermal SZ, results from cluster bulk motion through the CMB rest frame. Clusters moving toward Earth produce slight temperature increases from Doppler blue shifting of scattered photons, while clusters moving away produce decreases from redshifting. The kinematic SZ signal is proportional to cluster velocity and electron optical depth, allowing measurement of cluster peculiar velocities when combined with thermal SZ providing electron density. Stacking kinematic SZ signals from hundreds of clusters reveals bulk flows, coherent motions of cluster populations, testing cosmological models, predicting velocity fields from structure formation. The dark flow controversy emerged from kinematic SZ measurements, suggesting larger than expected bulk flows, though independent analyses using Planck data found weaker or null signals, leaving the issue unresolved. The integrated Sachs-Wolf effect describes CMB photon energy changes from passing through time-varying gravitational potentials during cosmic history. In a matter-dominated universe, gravitational potentials remain constant over density's potential wells, neither deepen nor shallow over time, producing no net energy change as photons traverse them. Energy gained falling in equals energy lost climbing out. However, dark energy causes potentials to evolve. Overdense regions collapse more slowly than expected from gravity alone, because dark energy's repulsion resists collapse, causing potentials to shallow over time. Photons passing through experience net blue shifting more energy gained entering deep potential than lost exiting shallower potential. Conversely, underdense voids expand faster than expected, deepening over time, causing photons to lose net energy. These late-time ISW effects imprint correlations between large-scale structure and CMB temperature, detected statistically by cross-correlating CMB maps with galaxy surveys. Anomalous temperature gradients in high redshift regions of the CMB refer to claims that temperature fluctuation statistics vary with distance to last scattering surface, potentially violating the assumption that recombination occurred uniformly at Z equals 1,100 everywhere. Some analyses suggest regions at different redshifts, corresponding to photons last scattering slightly earlier or later than 380,000 years, show systematically different fluctuation amplitudes or spectral properties. If confirmed, this would indicate recombination's timing or conditions varied spatially, perhaps from pre-inflationary inhomogeneities or exotic physics affecting ionization history. However, most studies find fluctuation statistics consistent with uniform recombination across the sky within uncertainties. Apparent variations might arise from subtle instrumental systematics, foreground contamination, or gravitational lensing effects that redistribute power between scales, creating illusions of distance-dependent statistics without genuine physical variation. Late-time ISW effect provides a direct probe of dark energy through correlations between CMB temperature and large-scale structure traced by galaxies, quasars, or gravitational lensing. The effect operates at redshifts Z less than 2, where dark energy becomes dynamically significant, causing structure evolution to depart from matter-dominated predictions. Statistical cross-correlation between CMB temperature maps and galaxy density maps reveals ISW signal hot CMB spots correlate with galaxy overdensities because photons gained energy falling into potentials that subsequently shallowed, while cold spots correlate with voids where photons lost energy. The correlation amplitude depends on dark energy's equation of state and evolution, with stronger dark energy producing larger ISW signals. Multiple studies using WMAP, Planck, and various galaxy surveys detected ISW correlations at 3 to 4 sigma significance, providing independent evidence for dark energy beyond supernovae and confirming its influence on recent cosmic history. Unexpected hot and cold spots not explained by known structures occasionally appear in CMB maps after removing acoustic oscillations, foregrounds, and known ISW contributions from mapped structures. These features might represent rare, large amplitude primordial fluctuations, several sigma peaks, allowed by Gaussian statistics, though rare, or could indicate unknown massive structures at specific redshifts not captured by current surveys. Alternatively, they might result from residual foreground contamination, instrumental artifacts, or lensing effects, creating apparent features without underlying physical temperature variations. Distinguishing these possibilities requires multi-frequency observations to test for foreground spectral signatures, independent confirmation using different instruments, and comprehensive modeling of expected signals from all known physical effects. Most apparent anomalous features dissolve upon careful analysis, though a few like the cold spot persist even after exhaustive investigation. Tensions between early universe measurements from CMB and late universe measurements from supernovae and baryon acoustic oscillations manifest primarily in the Hubble constant zero discrepancy. Planck CMB measurements combined with lambda CDM model predictions yield H0 equals 67.4 km per second per megaparsec. Late universe measurements using Cepheid variable stars to calibrate type Ia supernova distances yield H0 equals 73 km per second per megaparsec, disagreeing at 5 sigma significance probability less than 1 inch 3.5 million for random statistical fluctuation. This tension suggests either systematic errors in one or both measurements, or genuine breakdown of lambda CDM assumptions such as constant dark energy, zero spatial curvature, or general relativity on cosmological scales. Additionally, SATE parameter measuring matter clustering amplitude shows 2 to 3 sigma tension between Planck CMB and weak gravitational lensing measurements, suggesting possible issues with structure formation physics or neutrino masses. Gravitational lensing anomalies. Weak gravitational lensing describes the subtle distortion of background galaxy shapes by foreground mass distributions, detectable statistically by measuring correlations in galaxy ellipticities across millions of galaxies. Light from distant galaxies bends as it passes through gravitational potentials from foreground dark matter, galaxies and clusters, causing systematic tangential alignment of background galaxy images around foreground masses. The distortion is typically a few percent, far too small to notice in individual galaxies, but statistical analysis averaging over thousands to millions of galaxies reveals coherent lensing patterns tracing matter distribution. Weak lensing provides unique advantages for cosmology. It directly measures total mass, including dark matter, without relying on dynamical tracers or astrophysical assumptions about galaxy-dark matter relationships. It probes dark matter on scales from kiloparsecs to hundreds of megaparsecs, testing structure formation across cosmic history by measuring lensing at different redshifts. Strong gravitational lensing occurs when massive foreground objects like galaxy clusters or massive elliptical galaxies create sufficient curvature to produce multiple images of background sources, Einstein rings where source and lens align perfectly, or giant arcs stretching background galaxy images into elongated crescents. Strong lensing is observable in individual systems without statistical averaging, providing precise measurements of lens masses within Einstein radii typically hundreds of kiloparsecs for galaxy-scale lenses and megaparsecs for cluster lenses. Over 1,000 strong lens systems are known, including spectacular examples like the horseshoe Einstein ring, where a Z equals 2.5 galaxy is lensed by a Z equals 0.4 cluster, and the Einstein cross, where a single quasar at Z equals 1.7 produces 4 images around a Z equals 0.04 foreground galaxy. Strong lensing also enables time delay cosmography. Measuring time delays between images from lensing geometry provides independent H0 measurements, contributing to Hubble tension investigations. CMB lensing describes the deflection of cosmic microwave background photons by gravitational potentials from all structure between recombination and Earth, subtly remapping CMB temperature and polarization patterns. The deflection angle is typically a few arc-minutes far smaller than CMB features, but measurable statistically by analyzing how acoustic peaks and polarization patterns appear slightly smeared and distorted compared to unlensed predictions. Planck satellite measured CMB lensing across the full sky by reconstructing the lensing potential, the projected gravitational potential, along the line of sight from 4-point correlations in temperature and polarization maps. The lensing signal provides constraints on structure growth, dark energy, neutrino masses, and matter clustering amplitude SAT. Interestingly, Planck CMB lensing shows 2 to 3 sigma lower amplitude than predicted from Planck's best fit cosmology based on temperature and polarization power spectra alone, creating internal tension within CMB data. Lensing convergence maps reveal dark matter distribution by reconstructing surface mass density along lines of sight from observed lensing distortions. Weak lensing surveys measure galaxy ellipticities and correlate them to build convergence maps showing where mass concentrates. These maps directly visualize dark matter halos, filaments, and voids without relying on galaxies as tracers. The Kilo Degree Survey, Dark Energy Survey, and Hyper-Suprime Cam Survey have mapped dark matter across thousands of square degrees, revealing the cosmic web's structure and measuring matter clustering statistics. Comparing lensing-inferred mass distributions to galaxy distributions tests the relationship between dark and luminous matter. Anomalies appear when lensing suggests higher or lower mass than expected from galaxy counts or dynamical measurements, indicating either observational systematics or astrophysical complexity in how galaxies trace dark matter. Anomalies in gravitational lensing include excess signal in certain sky directions, systematic differences between lensing amplitude measured by different surveys or methods, and discrepancies between lensing masses and dynamical masses for clusters. Some studies report lensing overdensities regions showing stronger than expected lensing signal in specific directions, possibly indicating massive structures at particular redshifts or cosmic variance in our local region. The lensing amplitude from galaxy weak lensing surveys tends to yield lower S8 values around 0.76 to 0.78 than Planck CMB, which yields S8 equals 0.83, creating 2 to 3 sigma tension. This could indicate systematic errors in lensing shear measurements, photometric redshift uncertainties, intrinsic alignment contamination, or genuine cosmological signals such as modified gravity, massive neutrinos, or dark energy evolution affecting structure growth differently than lambda CDM predicts. The lensing is low problem refers to the observation that CMB lensing amplitude measured by Planck satellite is approximately 2 to 3 sigma lower than predicted by Planck's best fit lambda CDM model derived from temperature and polarization power spectra. This internal tension within Planck data suggests either systematic errors in lensing reconstruction, unaccounted foreground residuals affecting temperature, polarization spectra, or new physics modifying lensing amplitude relative to acoustic peak amplitudes. The discrepancy appears primarily at intermediate angular scales, multipoles L approximately 100 to 400, while matching predictions at larger and smaller scales. Proposed explanations include modified gravity models, suppressing lensing, massive neutrinos, reducing matter clustering, early dark energy or other extensions, to lambda CDM changing expansion history subtly, or statistical fluctuations, though 2 to 3 sigma significance makes flukes unlikely. Discrepancy between Planck CMB lensing and galaxy weak lensing compounds the problem by showing both measure lower lensing amplitude than expected from Planck CMB temperature, polarization, but also disagree with each other. Planck CMB lensing yields SATE approximately 0.8, intermediate between Planck primary CMBs 0.83 and galaxy weak lensing 0.76 to 0.78. This three-way disagreement suggests systematic errors likely plague at least one measurement, though which one remains unclear. Galaxy weak lensing faces challenges from shear calibration, accurately measuring small ellipticity distortions, intrinsic alignments, where galaxies align with tidal fields independent of lensing, photometric redshift errors, scattering galaxies between redshift bins, and baryonic feedback processes altering matter distribution on small scales. CMB lensing faces challenges from foreground contamination, particularly the cosmic infrared background from dusty galaxies correlating with lensing, and from uncertain modeling of secondary anisotropies. Resolving these tensions is top priority for observational cosmology. Possible solutions to lensing anomalies include systematic errors in observations, the most conservative explanation invoking unidentified biases in measurements rather than new physics. For galaxy-weak lensing, multiplicative shear biases of a few percent could reconcile tensions, achievable through improved calibration using image simulations, or improved photo-Z measurements using spectroscopic training samples. For CMB lensing, better foreground cleaning and secondary anisotropy modeling might resolve discrepancies. Alternatively, new physics could explain tensions. Modified gravity theories like FR gravity or DGP brainworld scenarios suppress lensing relative to expansion. Neutrino masses totaling 0.2 to 0.3 electron volts reduce matter clustering on small scales. Early dark energy models modifying pre-recombination expansion affect structure growth, or dark energy evolving with redshift changes structure formation history. Future surveys Rubin Observatory, Euclid, Roman will test these possibilities with improved precision and systematics control. Hubble tension, the expansion rate crisis. The Hubble constant zero quantifies the universe's current expansion rate, expressing how fast galaxies recede due to cosmic expansion as a function of distance. The constant's value, measured in kilometers per second per megaparsec, indicates recession velocity per unit distance. For example, h0 equals 70 means galaxies 1 megaparsec away recede at 70 kilometers per second. Galaxies 2 megaparsecs away recede at 140 kilometers per second, and so forth. Determining h0 precisely is crucial for cosmology because it sets the universe's age higher. h0 means faster expansion, and younger universe calibrates distance measurements throughout the cosmos and constrains dark energy properties. For decades, measurements carried significant uncertainties, yielding values anywhere from 50 to 100. By the 2000s, convergence seemed achieved around 70. However, increasingly precise measurements in the 2010 seconds revealed a disturbing split. Early, universe methods using cosmic microwave background yield h0 approximately 67, while late universe methods using supernovae and Cepheids yield h0 approximately 73, a 9% discrepancy significant at 5 sigma, meaning probability less than 1 inch 3.5 million that disagreement results from random statistical fluctuation. Planck satellite measurements of the cosmic microwave background, combined with lambda CDM model predictions, yield H0 equals 67.4 plus or minus 0.5 kilometers per second per megaparsec based on final 2018 data release. This value derives not from direct expansion measurement, but from fitting theoretical models to CMB acoustic peak positions, which depend on sound horizon size at recombination, angular diameter distance to last scattering surface, and expansion history connecting recombination to present. Lambda CDM model, with 6 parameters: baryon density, dark matter density, dark energy density, spectral index of primordial fluctuations, amplitude of fluctuations, and optical depth to reionization, fits CMB data exquisitely well. The best fit parameters predict specific expansion history, yielding H0 equals 67.4 as a derived parameter. The measurement's precision reflects CMB's extraordinary statistical power from millions of independent pixels and exquisite theoretical understanding of acoustic physics. However, this zero value assumes lambda CDM is correct. If the model is wrong, the inferred H0 could be biased. The SH0 program supernovae He0 for the equation of state led by Adam Rees uses Hubble Space Telescope observations of Cepheid variable stars in nearby galaxies to calibrate type Ia supernova distances, building a distance ladder extending to cosmological distances where Hubble expansion dominates peculiar velocities. Cepheids are pulsating stars whose periods relate tightly to intrinsic luminosity. Longer periods correspond to higher luminosities, allowing distance determination by measuring apparent brightness once period is observed. SH0 observed Cepheids in 19 galaxies that also hosted type Ia supernovae, calibrating supernova absolute magnitudes. This calibration applies to 300 plus supernovae at redshifts 0.01 to 0.15, where distances and redshifts jointly constrain He0. The 2022 SH0 results yield H0 equals 73.04 plus or minus 1.04 kilometers per second per megaparsec, differing from Planck by 5.3 sigma, a crisis level tension, indicating either systematic errors or new physics. The 5 sigma tension represents statistical significance beyond reasonable doubt. In most sciences, particle physics uses 5 sigma as discovery threshold, and medical trials would decisively reject hypotheses at such levels. In cosmology context, 5 sigma means if Planck and SH0 measurements were both unbiased and uncorrelated, probability of disagreement this large by chance is 1 inch 3.5 million. Such low probability suggests 3 possibilities. Systematic errors bias one or both measurements more severely than estimated uncertainties account for. The measurements are somehow correlated through shared systematics, despite using completely different data and methods. Or lambda CDM cosmology is wrong, requiring new physics to reconcile observation. The first possibility, systematics, is most conservative and actively investigated. The second, correlations, seems implausible given different observational techniques, wavelengths, instruments, and analysis pipelines. The third, new physics, excites theorists, but requires caution given cosmology's history of apparent crises, dissolving upon better understanding of systematics. Early universe measurements using cosmic microwave background and baryon acoustic oscillations infer He0 from physics at redshifts Z approximately 1000 to 3, extrapolating to present using theoretical models. CMB measures conditions at Z equals 1000, 100, when universe was 380,000 years old. Baryon acoustic oscillations, imprints of sound waves in matter distribution, visible as characteristic 150 megaparsec scale in galaxy clustering probe redshifts Z less than 3, typically 0.5 to 2.5 inches current surveys. These methods don't measure expansion directly at Z equals 0, but infer it through model-dependent extrapolation, assuming lambda CDM. They're powerful because early universe physics is simple, well understood, based on particle physics, and thermodynamics and measurements have exquisite precision. But accuracy depends entirely on model correctness. If dark energy evolves rather than being constant, cosmological constant, if neutrino masses differ from assumptions, if spatial curvature is non-zero, or if unknown physics operates, the extrapolated H0 could be systematically wrong despite precise measurements. Late universe measurements using type Ia supernovae, Cepheid variables, and tip of the red giant branch stars determine H0 from observations at redshifts Z less than 0.15, close to the present epoch. These methods build distance ladders, nearby distances measured geometrically through parallax, intermediate distances through Cepheids or TRGB stars whose intrinsic luminosities are calibrated, and cosmological distances through type Ia supernovae whose peak brightness standardizes through empirical width-luminosity relations. The ladder's advantage is model independence, few cosmological assumptions required, mostly just assuming Euclidean geometry on small scales and homogeneous expansion on large scales. Disadvantages include systematic error accumulation through ladder rungs errors in parallax, affect Cepheid calibration, which affects supernova calibration, which affects H0 and potential astrophysical systematics like metallicity-dependent Cepheid periods, supernova evolution with redshift, or extinction corrections. Nevertheless, multiple independent late universe methods SH0ES, Carnegie Supernova Project, Pantheon sample yield consistent H0, approximately 73, reinforcing confidence despite systematics concerns. Implications of the Hubble tension are profound if the discrepancy is real rather than systematic. New physics would be required to modify either early universe conditions affecting CMB inferred H0 or late universe expansion affecting local measurements. Possibilities include early dark energy, a component dynamically important before recombination, but negligible today, reducing sound horizon size and increasing inferred H0 from CMB. Alternatively, late-time modifications like evolving dark energy, interactions between dark energy and dark matter, or modified gravity-changing expansion history between recombination and present could reconcile measurements. More exotic proposals invoke extra radiation like sterile neutrinos, varying fundamental constants, or primordial magnetic fields. Each proposal must satisfy stringent constraints from other observations: Big Bang nucleosynthesis, structure formation, weak lensing, making simple solutions difficult. Some researchers question whether we live in a local void, reducing our local H0, though simulations suggest voids large enough would violate other constraints. The local void hypothesis proposes that the Milky Way resides in a 300 million light-year diameter underdense region, a void causing locally reduced expansion rate compared to cosmic average. In voids, less matter means weaker gravitational deceleration, allowing faster expansion. But we observe from inside, measuring local H0 that's higher than cosmic average would be. Wait, that's backwards. Actually, voids expand faster internally, but galaxies on void edges experience inward peculiar velocities as they fall towards surrounding overdensities. This reduces their recession velocities, lowering observed H0 locally. A large enough void could reduce local H0 by several percent. However, simulations and observations constrain void size and depth. A void reducing H0 by 9% would need to be 500+ million light-years across and 30+% underdense, producing observable effects on supernova distances, CMB lensing, and kinematic SZ that aren't seen. Most cosmologists consider the void hypothesis unlikely to fully explain the tension, though it might contribute several percent effect. The KBC void controversy. The KBC void, named after discoverers Keenan, Barger, and Cowie, who published findings in 2013, proposes that the local group resides near the center of an enormous underdense region extending approximately 2 billion light-years in diameter, nearly 25% the observable universe's size and far exceeding the approximately 300 to 400 million light-year homogeneity scale predicted by lambda CDM. If confirmed, this would represent the largest known structure and challenge fundamental cosmological assumptions about uniformity. The proposal emerged from galaxy number counts, showing systematic deficit to redshift Z approximately 0.1, corresponding to roughly 1 billion light-years, with density 20 to 30% below cosmic average. Such enormous voids shouldn't exist according to standard structure formation. They'd require initial density fluctuations far larger than observed in the CMB, or would need impossibly long formation times exceeding the universe's age. The controversy centers on whether the underdensity is real or results from selection effects, incomplete sampling, and cosmic variance in local region. The original 2013 paper analyzed galaxy luminosity functions, the number density of galaxies at different brightness levels, comparing local region within 350 million light-years to distant regions beyond 1 billion light-years serving as cosmic average. The analysis found 20 to 40% deficit in galaxy counts locally, depending on luminosity bin, with effect strongest for bright galaxies. Subsequent studies extended analysis to Z approximately 0.1 using spectroscopic galaxy surveys, confirming systematic underdensity at that level. The underdensity's radial profile appears to increase from Milky Way outward, reaching maximum around 300 to 500 million light-years, then transitioning to average density beyond 1 billion light-years. If interpreted as a single coherent void, the structure would span roughly 2 billion light-years, with the local group positioned off-center toward one edge rather than precisely centered. The void's shape appears irregular rather than spherical, consistent with cosmic voids' typical complex morphologies. If the KBC void is real, it represents a structure exceeding lambda CDM's predicted maximum sizes by factor 5 to 10. Cosmological principle predicts homogeneity emerges at 300 to 400 million light-year scales, where density fluctuations average to cosmic mean. Structures substantially larger violate this expectation, requiring either extremely rare fluctuations occurring in less than 0.01% of cosmic volumes, or indicating that lambda CDM underestimates large-scale structure amplitude. Simulations using standard cosmology occasionally produce voids approaching 500 million light-years, but rarely exceed this. A 2 billion light-year void would be extraordinarily rare, expected in perhaps 1 per 100 observable volumes. The probability of finding ourselves inside such a rare fluctuation is low. Anthropic selection doesn't favor voids, since galaxies and stars form fine in average density regions. This low probability makes cosmologists skeptical absent overwhelming evidence. The KBC void could potentially explain the Hubble tension if living in a large void reduces our local expansion rate compared to cosmic average. Voids expand faster internally than surrounding regions because less matter means weaker gravitational deceleration. However, this creates an inward peculiar velocity field. Galaxies on void edges fall towards surrounding overdensities, reducing their recession velocities relative to Hubble expansion. Observers inside voids therefore measure lower H0 than the cosmic average. Quantitative models show that a 300 million light-year void with 20 to 30% underdensity could reduce local H0 by 2 to 3%, helpful, but insufficient to explain the 9% Planck SH0 ES discrepancy. A 2 billion light-year void with 20 to 30% underdensity could potentially reduce H0 by 5 to 7%, substantially alleviating tension. This tantalizing possibility has motivated detailed investigation, though most studies conclude void effects fall short of fully resolving tension. Controversy surrounding the KBC void centers on whether comprehensive galaxy surveys like Sloan Digital Sky Survey confirm or refute the claimed underdensity. SDSS mapped over 900,000 galaxy spectra across 10,000 square degrees to redshift Z approximately 0.2, providing unprecedented three-dimensional structure maps. Multiple independent analyses of SDSS data failed to find evidence for 2 billion light-year scale underdensity around the local group. Some studies find modest underdensity, 10 to 15% deficit to Z approximately 0.05, consistent with known local voids like the local void, but no evidence for giant void extending to Z equals 0.1 or beyond. The discrepancy between studies might arise from different sample selections. KBC used specific galaxy types and luminosity cuts, while SDSS analyses used volume-limited samples, different statistical methods, or genuine cosmic variance in different sky regions, since surveys don't cover identical volumes. Selection effects and incomplete sampling could create apparent voids through observational biases rather than genuine underdensity. If surveys preferentially miss faint galaxies in certain redshift ranges due to magnitude limits, surface brightness selection, or fiber collision effects where nearby galaxy spectra can't be obtained simultaneously, the resulting catalogues would show artificial underdensities. Additionally, cosmic variance statistical fluctuations from observing finite volumes become significant when comparing local region to distant regions if volumes aren't matched carefully. The local region is observed completely. All bright galaxies within 300 million light-years are catalogued, while distant comparison regions are sampled sparsely. This asymmetric sampling could bias comparisons. Photometric redshift errors scattering galaxies between redshift bins could also create apparent voids. Careful accounting for these effects is crucial, but different studies reach different conclusions about their importance. Most cosmologists remain skeptical about the KBC void pending confirmation from upcoming surveys, including the Dark Energy Spectroscopic Instrument, measuring 35 million galaxy spectra, and Euclid satellite imaging billions of galaxies. DESI's spectroscopic survey will map galaxy distribution to Z approximately 2 with unprecedented completeness, definitively testing whether large-scale underdensity exists locally. Euclid's photometric redshifts for billions of galaxies will complement DESI, providing independent void measurements through weak lensing. If a giant void exists, its reduced mass would produce measurably weaker lensing convergence. Current evidence from SDSS and other surveys leans against a 2 billion light-year void, suggesting either the claimed underdensity is artifact of selection effects, or at most the void is 300 to 500 million light-years large, but not extraordinary, rather than 2 billion light-years. Consensus awaits DESI and Euclid results. The KBC void relates to cosmic variance statistical fluctuations arising from observing finite volumes. Even if the universe is statistically homogeneous on large scales, any finite volume shows fluctuations around the mean. Our observable universe, though vast, is finite, a 93 billion light-year diameter sphere, and thus exhibits cosmic variance. We might live in an atypical region by pure chance, though probabilities constrain how atypical. Living in a 2 sigma fluctuation, 2 standard deviations from mean, has probability 5%, uncomfortably low but not impossible. A 3 sigma fluctuation has probability 0.3%, straining credulity unless anthropic selection favors such regions. The KBC void, if real, would represent 3 to 4 sigma fluctuation based on lambda CDM predictions, making it extraordinarily rare but not impossible. The philosophical question is whether invoking rare fluctuations is more palatable than accepting new physics, or whether rare fluctuations simply signal model inadequacy. Large quasar groups, extreme structures. The huge large quasar group, abbreviated huge LQG, represents a concentration of 73 quasars at redshift Z, approximately 1.27, distributed across roughly 4 billion light-years, 1.2 gigaparsecs, making it potentially the largest known structure in the universe, when discovered in 2013 by Roger Clowes and colleagues. Quasars are the luminous cores of actively accreting supermassive black holes. Predominantly observed at redshifts Z equals 1 to 3, corresponding to cosmic epochs 7 to 10 billion years ago, when merger rates and gas supplies peaked. While individual quasars are rare, only one per several hundred million cubic light-years, they cluster gravitationally into groups tracing underlying dark matter overdensities, just as galaxies cluster. Large quasar groups contain dozens to hundreds of quasars spread across hundreds of millions of light-years, representing massive overdense filaments or walls in the cosmic web. The huge LQG's 4 billion light-year extent exceeds the cosmological principle's homogeneity scale by factor 10, challenging predictions that structure amplitude should decrease rapidly on scales exceeding 500 million light-years. Discovery occurred through systematic analysis of quasar positions from large spectroscopic surveys, including the Sloan Digital Sky Survey's quasar catalogue, containing over 500,000 quasars. Researchers applied friend-of-friend algorithms, identifying quasar pairs separated by less than linking length threshold, and connecting them into groups, with linking length chosen based on expected quasar clustering, lambda CDM simulations. The huge LQG emerged as an unusually extended chain of connected quasars stretching 4 billion light-years in its longest dimension, containing 73 members concentrated in a filamentary or web-like structure. The group's characteristic size, defined through various statistical measures, including spatial extent and minimum spanning tree, consistently yields values 1 to 1.5 gigaparsecs. This vastly exceeds typical large quasar groups, which span 100 to 500 megaparsecs. The discovery paper calculated probability less than 0.001% of finding such large structure in lambda CDM simulations, suggesting extraordinary rarity or challenge to standard model. The probability calculation, indicating less than 0.001% chance, stems from comparing observed structure to predictions from lambda CDM cosmological simulation. Simulations generate mock quasar catalogues matching observed quasar number density, clustering properties, and selection functions, then apply identical friend-of-friend algorithms to search for large quasar groups. Across millions of simulated volumes equivalent to survey size, groups as large as the huge LQG appear in less than 0.001% of realizations, roughly 1 inch 100,000 volumes. This extremely low probability suggests either extraordinary luck in finding such rare fluctuation or systematic differences between reality and simulation. Possible differences include quasar clustering being stronger than lambda CDM predicts, perhaps due to underestimated bias quasars might trace overdensities more strongly than simulations assume, or actual structure amplitude on gigaparsec scales exceeding predictions, indicating breakdown of cosmological principle or need for modified cosmology. If the huge LQG is real as a coherent structure, it fundamentally challenges the cosmological principle by exceeding predicted maximum structure size by order of magnitude. Lambda CDM predicts structures cease growing coherently beyond 300 to 500 megaparsecs, where density fluctuations average to uniformity. Larger apparent structures should represent chance alignments of separate smaller structures along line of sight rather than gravitationally bound or dynamically coherent entities. The huge LQG's 1.2 gigaparsec size thus seems incompatible with homogeneity emerging at 300 megaparsec scales. Explanations include: the quasars aren't genuinely associated, but coincidentally aligned in projection without physical connection. Statistical tests attempt to rule this out, but projection effects are subtle. The structure represents multiple connected filaments, creating apparent coherence without single-bound entity. Cosmic web simulations show this is plausible. Or cosmological principle breaks down, with structure continuing to scales approaching observable universe size, requiring modified cosmology or inflation. The Hercules Corona Borealis Great Wall, announced in 2013 based on gamma-ray burst distributions, purports to be even larger, potentially 10 billion light-years across, spanning roughly 10% of the observable universe's diameter. Lajos Balaz and colleagues identified clustering of gamma-ray bursts at redshift Z approximately 2, separated by angular distances corresponding to several gigaparsecs if at same redshift. If these bursts trace a coherent structure like a massive supercluster or filament, it would dwarf all other known structures. However, the claim is extremely controversial. Gamma-ray bursts are difficult distance indicators. Redshift measurements exist for only subset, and bursts scatter widely in three-dimensional space, making structure identification challenging. Most cosmologists are skeptical, noting that statistical tests finding the association depend sensitively on chosen parameters and suffer from look elsewhere effect. Searching for any unusual pattern increases probability of finding something purely by chance. The Hercules Corona Borealis Great Wall controversy centers on statistical significance and physical plausibility. The original discovery paper reported statistically significant clustering at 4 to 5 sigma using certain correlation function analyses. However, independent studies applying different statistical methods found weaker or non-significant signals, suggesting original detection might result from particular analysis choices or statistical fluctuations enhanced by selective reporting. Even if gamma-ray bursts cluster as claimed, interpreting this as coherent 10 billion light-year structure requires assumptions about what constitutes structure. Is it merely enhanced density along line of sight or dynamically connected? Physically, a 10 billion light-year structure seems implausible in lambda CDM. Formation timescales would approach universe's age, and structure amplitude would require initial fluctuations orders of magnitude larger than CMB shows. Most researchers consider Hercules Corona Borealis Great Wall unconfirmed pending better data and independent verification. Both the huge LQG and Hercules Corona Borealis Great Wall, if confirmed, would severely challenge lambda CDM cosmology by violating predicted homogeneity scales. The cosmological principle isn't arbitrary assumption, but prediction from inflation. Quantum fluctuations during inflation created density fluctuations with power spectrum decreasing on large scales, ensuring rapid convergence to uniformity beyond 300 to 500 megaparsecs. Structures 4 to 10 billion light-years would require either extremely rare high sigma fluctuations, so rare that finding one in our observable volume seems incredibly lucky, or breakdown of inflation's predictions, perhaps indicating non-Gaussianity in fluctuations, anisotropic inflation, or alternative structure formation mechanisms. Alternatively, these structures might not be real artifacts of selection effects, projection, or statistical flukes. Current consensus leans towards skepticism, pending additional evidence, but unease remains about whether lambda CDM fully explains larger scale structure. Cosmic voids as dark energy laboratories. Cosmic voids, the underdense regions comprising 50 to 70% of the universe's volume, yet containing only 10 to 20% of galaxies, provide unique laboratories for testing dark energy physics because void expansion is particularly sensitive to dark energy's equation of state and evolution. Voids expand faster than average cosmic expansion. Their low density means weaker gravitational deceleration, allowing expansion to proceed nearly unimpeded, with expansion rate depending critically on dark energy properties. If dark energy is cosmological constant with equation of state W equals -1, voids expand at specific rate predictable from simulations. If dark energy evolves with W varying from -1, or if modified gravity rather than dark energy explains cosmic acceleration, void expansion rates differ detectably from lambda CDM predictions. Measuring void sizes, shapes, expansion rates, and abundance as functions of redshift thus constrains dark energy independently of supernovae, baryon acoustic oscillations, or weak lensing, providing crucial cross-checks and breaking degeneracies between cosmological parameters. Cosmic voids as dark energy laboratories. Cosmic voids, the underdense regions comprising 50 to 70% of the universe's volume, yet containing only 10 to 20% of galaxies, provide unique laboratories for testing dark energy physics because void expansion is particularly sensitive to dark energy's equation of state and evolution. Voids expand faster than average cosmic expansion. Their low density means weaker gravitational deceleration, allowing expansion to proceed nearly unimpeded, with expansion rate depending critically on dark energy properties. If dark energy is cosmological constant with equation of state W equals -1, voids expand at specific rate predictable from simulations. If dark energy evolves with W varying from -1, or if modified gravity rather than dark energy explains cosmic acceleration, void expansion rates differ detectably from lambda CDM predictions. Measuring void sizes, shapes, expansion rates, and abundance as functions of redshift thus constrains dark energy independently of supernovae, baryon acoustic oscillations, or weak lensing, providing crucial cross-checks and breaking degeneracies between cosmological parameters. Voids range from 30 to 500 million light-years in diameter, with typical sizes 100 to 200 million light-years. They're not completely empty, but extremely underdense matter. Density reaches only 10 to 20% of cosmic average in typical voids. The largest known voids exceed 300 million light-years. Void shapes are generally elongated rather than spherical, reflecting the cosmic web's filamentary geometry. Voids form between filaments and walls, taking on irregular polyhedral shapes. Void number density and size distribution evolve with cosmic time at high redshift. When the universe was younger and denser, voids were smaller and less numerous. As structure grew through gravitational instability, overdense regions accreted matter while underdense regions evacuated, causing voids to expand and merge. Measuring void statistics at different redshifts traces this evolution, which depends sensitively on dark energy driving late-time accelerated expansion. The Buyutes void, discovered in 1981 by Robert Kirshner and colleagues during galaxy redshift surveys, remains one of the most prominent known voids. spanning approximately 330 million light-years in diameter and centered roughly 700 million light-years from Earth. The void contains only 60 identified galaxies, compared to 3,000 expected from cosmic average density 98% depletion. Early observations dubbed it the Great Void due to its extraordinary emptiness. Subsequent deep surveys revealed the 60 galaxies aren't uniformly distributed, but cluster along void edges and in small filaments threading the void interior, demonstrating that even the emptiest regions show hierarchical structure. The few void galaxies show distinctive properties, predominantly late-type spirals and irregulars with active star formation, blue colors from young stellar populations, and high gas fractions. These galaxies avoided the environmental processing, affecting galaxies in filaments and clusters, evolving in isolation. Dark energy effects are stronger in underdense regions because dark energy's repulsive influence opposes gravity, and voids have minimal gravity to counteract it. In overdense regions like clusters, strong gravity from concentrated mass partially offsets dark energy's repulsion, slowing acceleration. In voids, weak gravity provides little resistance, allowing dark energy to drive expansion more effectively. This differential acceleration causes voids to expand faster than average, with expansion rate depending on dark energy's strength and evolution. Simulations show that if dark energy's equation of state parameter W becomes more negative, stronger repulsion void expansion accelerates dramatically, increasing void sizes and decreasing galaxy content. Conversely, if W approaches -0.8 or higher, weaker repulsion voids expand more slowly and remain smaller. Measuring void properties across cosmic time thus constrains W and its possible redshift evolution WZ, providing tests of whether dark energy is truly cosmological constant or evolving quintessence field. The Alcock-Pazinski test uses void shapes to constrain cosmological parameters through geometric distortion. Voids form from roughly isotropic initial fluctuations, so in real space they should have similar dimensions along and perpendicular to the line of sight. However, converting observed angular sizes and redshift extent to physical dimensions requires assuming cosmological model wrong. Cosmology produces systematically distorted shapes. For example, if true expansion history differs from assumed lambda CDM, distances inferred from redshifts will be wrong, making spherical voids appear elongated or flattened. Measuring shapes of many voids statistically determines which cosmology produces isotropic distributions, constraining dark energy density and equation of state. This test is powerful because it's geometric rather than depending on astrophysical assumptions about galaxy formation or evolution. Challenges include defining void boundaries precisely and correcting for peculiar velocities that distort redshift space positions. Void abundance, the number density of voids per comoving volume as function of void size, is sensitive to dark energy equation of state because dark energy affects structure growth rates. Stronger dark energy suppresses structure formation by accelerating expansion before gravity can collapse over densities, producing fewer and smaller voids at given redshift. Weaker dark energy allows more structure growth, creating larger and more numerous voids. Measuring void abundance at redshifts Z equals 0.5, 1, and 1.5 traces how void population evolved as dark energy's influence grew from negligible at high redshift to dominant today. Comparing observed void abundances to predictions from simulations with different W values constrains dark energy properties. Current surveys like BOSS and eBOSS measured void catalogues containing thousands of voids to Z, approximately 0.8. Future surveys DESI Euclid Roman will extend to Z, approximately 2, with larger samples, improving constraints significantly. Void galaxies show distinctive properties reflecting their isolated evolution. Spectroscopic observations reveal higher gas fractions ratio of gas mass to stellar mass, compared to filament or cluster galaxies of similar stellar mass. This reflects reduced ram pressure stripping and strangulation that remove gas from galaxies in dense environments. Void galaxies also show bluer colors, indicating younger stellar populations and higher specific star formation rates. Star formation rate divided by stellar mass. Their morphologies are predominantly late-type spirals and irregulars, with ellipticals rare, contrasting with cluster cores dominated by ellipticals. These differences demonstrate environment's profound impact on galaxy evolution. Studying void galaxies provides control samples representing what galaxies look like without environmental processing, allowing isolation of environmental effects by comparing to matched filament and cluster samples. The integrated Sachs-Wolf effect from voids creates CMB cold spots, where photons lost energy traversing expanding voids that deepen during transit due to dark energy. Measuring ISW signal from voids tests dark energy by cross-correlating void positions with CMB temperature. Stacking CMB temperature at positions of thousands of voids from galaxy surveys reveals average temperature profile characteristic cold central region surrounded by slightly warm ring where void boundaries compress. The signal amplitude depends on void size, depth, and dark energy properties. Observations using WMAP, Planck, and void catalogues from SDSS detected ISW void signal at 2 to 3 sigma significance, consistent with lambda CDM predictions. Future surveys with better CMB polarization data and larger void catalogues will improve detection significance and constrain dark energy equation of state through ISW amplitude measurement. The Eridanus supervoid and isodeficit. The Eridanus supervoid, discovered in 2015 by Istvan Sapudi and colleagues through galaxy survey analysis targeting the region aligned with the CMB cold spot, extends approximately 1.8 billion light-years in diameter, centered at redshift Z approximately 0.22, corresponding to distance roughly 2.5 billion light-years. Galaxy number counts in this region show 20 to 30% underdensity, compared to cosmic average significantly depleted, but not as extreme as the Botas void's 98% depletion. The void is large but not unprecedented simulations produce voids of this scale in roughly 1 to 2% of cosmic volumes, making it rare but allowed within lambda CDM. The supervoid's importance stems from its alignment with the CMB cold spot in constellation Eridanus, suggesting potential causal connection. CMB photons observed today passed through this region 6 to 7 billion years ago, when the void was forming, potentially imprinting temperature deficit through the integrated Sachs-Wolf effect. The void's location at Z approximately 0.2 places it at co-moving distance roughly 900 megaparsecs or 2.9 billion light-years, though angular diameter distance relevant for observational angular size is smaller, at approximately 750 megaparsecs or 2.4 billion light-years due to cosmic expansion. The void's angular extent on sky is roughly 15 to 20 degrees, encompassing the CMB cold spot's 10-degree diameter with margin. Three-dimensional mapping using spectroscopic redshift surveys, including 2-mass redshift survey and 6 DF galaxy survey, revealed the void's structure not a simple spherical underdensity, but complex network of smaller voids, low-density regions connected by minimal filaments. The galaxy deficit is most pronounced in the void's central region, aligned with the cold spot center, strengthening the association. However, the void's boundaries are diffuse rather than sharply defined, making size estimates somewhat uncertain depending on density threshold chosen to define void edges. Galaxy counts showing 20 to 30% underdensity mean this region contains 70 to 80% of expected galaxy numbers based on cosmic average. This translates to matter underdensity total mass, including dark matter of similar magnitude, assuming galaxies trace mass reasonably well. Some studies suggest matter underdensity might be slightly less than galaxy underdensity if galaxies in voids have lower bias trace over densities less strongly than average, though observational evidence for this is mixed. The underdensity extends across the void's 1.8 billion light-year diameter, representing significant mass deficit totaling roughly 10 to the 16th to 10 to the 17th solar masses, compared to average density region of same volume. This missing mass gravitationally affects photon trajectories, structure formation in surrounding regions, and expansion dynamics locally, making the supervoid dynamically significant despite being underdense rather than overdense. The alignment with the CMB cold spot is spatially coincident. The void center lies within a few degrees of the cold spot's center when projected on the sky, and the void's angular size matches the cold spot's extent. Temporal alignment is also favorable. CMB photons observed today left the last scattering surface 13.8 billion years ago and traversed the region where the Eridanus supervoid now exists approximately 6 to 7 billion years ago, corresponding to redshift Z approximately 0.7 to 0.5. At that epoch, the protovoid was forming through gravitational evacuation as matter flowed towards surrounding overdensities. The ISW effect operates most strongly during epochs, when structure evolution is fastest, which occurs during matter to dark energy transition around redshift Z approximately 1 to 0.5, when dark energy's influence grows from negligible to dominant. The Eridanus supervoid formed precisely during this critical epoch, maximizing ISW signal. The ISW effect predicts temperature deficit of 10 to 20 microkelvin for a void of the Eridanus supervoid size and depth based on standard calculations. The prediction comes from integrating Sachs-Wolf formula over photon paths through the void, accounting for void's gravitational potential depth, expansion rate, and dark energy influence. A 1.8 billion light-year void with 25% matter underdensity creates gravitational potential anomaly difference from average density region of order 10 to the minus 6 inches dimensionless units. Photons traversing this potential lose fractional energy equal to potential change, approximately 10 to the minus 6, corresponding to temperature change 10 to the minus 6 times 2.725 Kelvin equals 3 microkelvin. However, dark energy enhancement factor photons exiting shallower potential than entered amplifies this by factor 3 to 5, depending on exact void profile and dark energy equation of state, yielding predicted deficit 10 to 20 microkelvin. The observed cold spot shows 70 microkelvin deficit at its coldest point, 3.5 times larger than the 10 to 20 microkelvin predicted from the Eridanus supervoid alone. This discrepancy is the core mystery. If the supervoid fully explains the cold spot, the ISW prediction is too small by factor 3.5, suggesting either the void is deeper or larger than measured. Multiple voids align along the line of sight, compounding ISW effects, or non-standard physics enhances ISW beyond lambda CDM predictions. Alternatively, the supervoid provides only partial explanation, contributing 20 to 30% of the cold spot's amplitude, with remaining 50 microkelvin arising from primordial fluctuations, texture defect, or other physics. Statistical analyses calculate probability of primordial 50 microkelvin fluctuation as roughly 1 inch 100 low, but not impossible, compared to 1 inch 1000 for full 70 microkelvin fluctuation. If the supervoid contribution is real, this makes the cold spot marginally consistent with lambda CDM, though still unusual. Alternative explanations for the full cold spot amplitude include multiple voids aligned along the same line of sight, creating compound ISW effect. If 2 or 3 voids of moderate size 300 to 500 million light-years align at different redshifts along the Eridanus direction, their ISW contributions add, potentially producing 70 microkelvin total deficit. However, finding such specific alignment seems contrived. Voids are common, but having multiple specifically along one sightline is unlikely. Another possibility is that the Eridanus supervoid is colder or denser than estimates suggest. If central underdensity reaches 40 to 50% rather than 20 to 30% possible, if faint galaxies are undercounted, or if galaxy bias is weaker than assumed, the ISW prediction increases proportionally, potentially explaining the full signal. Deep galaxy surveys targeting the void region could test this by searching for previously uncounted faint galaxies. Cosmic textures, topological defects formed during symmetry-breaking phase transitions in the early universe, provide an alternative explanation independent of voids. Textures are localized field configurations that form, evolve, and decay, releasing energy that perturbs matter and radiation. Texture decay imprints characteristic CMB temperature pattern central cold spot, surrounded by hot ring, matching the cold spot's observed morphology in some analyses. The texture scenario predicts specific correlations between temperature and polarization distinct from primordial fluctuations or ISW signatures, potentially testable with Planck polarization data. However, detailed Planck analyses found no convincing texture signature, and cosmological constraints from CMB power spectrum limit texture contributions to less than few % of total fluctuations, making individual large texture features difficult to explain. Most cosmologists consider texture explanations speculative without stronger evidence. The multiverse collision hypothesis, proposed by Laura Mersini-Houghton, suggests the cold spot results from bubble universe collision during eternal inflation. In this scenario, our universe is one bubble nucleating from eternally inflating space, occasionally colliding with neighboring bubbles. Collisions imprint circular temperature patterns on the CMB, typically cold spots at collision centers. Mersini-Houghton predicted such signatures before WMAP data release, claiming the cold spot as confirmation. However, systematic searches for circular temperature patterns in Planck data found no statistically significant collision signatures matching theoretical predictions. The cold spot's elongated irregular morphology differs from collision-predicted circular symmetry. Most cosmologists remain skeptical of multiverse collision hypothesis as cold spot explanation, though the broader eternal inflation paradigm has theoretical support. Definitive tests require independent multiverse collision evidence beyond CMB anomalies alone, modified gravity theories at cosmic scales. General relativity has been tested to extraordinary precision in the solar system through planetary orbits, light deflection, gravitational redshift, gravitational time delay, and binary pulsar orbital decay from gravitational wave emission. These tests confirm GR's predictions to better than 0.1% in most cases, with binary pulsar measurements matching GR to parts per thousand. However, cosmological applications extrapolate GR over 28 orders of magnitude in scale, from solar system's astronomical unit to cosmological horizons billions of light-years, and over enormous range in curvature, from weak solar system fields to strong fields near black holes and in early universe. Such extrapolation might break down if GR is effective theory valid only in certain regimes. Modified gravity theories propose deviations from GR at very large scales or very weak accelerations, potentially explaining cosmic acceleration without dark energy, or resolving tensions between observations and lambda CDM predictions. Mund-modified Newtonian dynamics proposed by Mordechai Milgram in 1983 modifies Newton's second law F equals ma at extremely low accelerations below roughly 10 to the minus 10 meters per second squared, replacing it with F equals m times a squared divided by a0, where a0 is a fundamental acceleration scale. This modification explains galaxy rotation curves without dark matter stars in galaxy outskirts experience accelerations below a zero, entering Mund regime where gravity weakens less rapidly than Newtonian inverse square law, providing additional centripetal force that flattens rotation curves. Mund successfully predicts rotation curves for hundreds of galaxies using single parameter A0, approximately 1.2 times 10 to the minus 10 meters per second squared. However, Mund faces challenges, explaining cluster dynamics. Clusters require dark matter, even in Mund, and lacks relativistic formulation needed for cosmology, light deflection, and gravitational wave propagation. Tv's tensor vector scalar gravity, developed by Jacob Bekenstein in 2004, provides relativistic extension of Mund incorporating tensor metric field like GR plus vector and scalar fields, producing Mund-like effects. Tevez reproduces Mund's galaxy rotation curve successes while allowing gravitational lensing, cosmological expansion, and gravitational wave prediction. However, Tevez predicts gravitational waves propagate at a different speed than light due to scalar field coupling, contradicting observations from neutron star merger GW170817, where gravitational waves arrive simultaneously with gamma rays after traveling 130 million light-years. This 1-second arrival difference over 130 million year journey constrains wave speed to within 10 to the minus 15th fractional difference from light speed, essentially ruling out Tevez and similar theories where gravitational wave speed differs significantly from light speed. FR gravity modifies Einstein-Hilbert action by replacing Ricci scalar r with function FR, allowing curvature-dependent gravitational coupling. Simple models include FR equals r plus alpha over r, where alpha is parameter with dimensions length squared. Such modifications can drive cosmic acceleration without cosmological constant, when space-time curvature becomes very small, as in present universe's expansion, the alpha over r term dominates, mimicking dark energy. FR models face fine-tuning challenges, requiring specific FR forms to match expansion history while satisfying solar system tests and avoiding instabilities. They also predict fifth forces from additional scalar degree of freedom, constrained by laboratory tests and astrophysical observations. Some FR models survive all tests through screening mechanisms that suppress modifications in high-density environments like solar system while allowing them cosmologically, but distinguishing these from lambda CDM observationally requires precision tests of structure growth and weak lensing. Massive gravity assigns mass to the graviton, the hypothetical quantum of gravitational field, modifying gravitational force law at very large distances. In general relativity, gravitons are massless, making gravity exactly inverse square and infinite ranged. If gravitons have tiny mass below 10 to the minus 32 electron volts from current constraints, gravity transitions from inverse square to exponential decay beyond Compton wavelength, roughly c divided by graviton mass. For graviton masses around 10 to the minus 33 electron volts, the Compton wavelength equals the Hubble radius roughly 10 billion light-years, producing modifications on cosmological scales while preserving GR locally. Massive gravity can explain cosmic acceleration the graviton mass term mimics dark energy without introducing cosmological constant. However, most massive gravity theories suffer from instabilities like Boole-Ware-Dieser ghost negative energy states, causing vacuum decay unless carefully constructed. Recent, healthy, massive gravity models avoid ghosts, but still face challenges matching observational expansion history. Tensions between modified gravity and observations appear most starkly in the Bullet cluster 1E0657-56, where colliding galaxy clusters show spatial offset between hot X-ray emitting gas and gravitational lensing mass. X-rays trace baryonic matter, while lensing traces total mass, including dark matter. The offset demonstrates dark matter passed through collision unimpeded, while baryonic gas collided and stopped through electromagnetic interactions. Mund and similar theories modifying gravity without dark matter cannot explain this gravity should trace baryons, yet lensing peaks lie displaced from baryonic peaks by several hundred kiloparsecs. Dark matter provides natural explanation. Dark matter halos passed through each other collisionlessly while gas collided. Modified gravity theories must either introduce dark matter anyway, negating motivation, or invoke extreme fine-tuning of modifications to mimic dark matter distributions. Most cosmologists consider Bullet cluster strong evidence for dark matter's reality over modified gravity alone. Screening mechanisms suppress modifications to GR in high-density environments, while allowing them cosmologically, potentially reconciling modified gravity with solar system tests. The chameleon mechanism gives scalar field mass depending on local matter density. High density produces heavy scalar field with short Compton wavelength suppressing fifth forces, while low density produces light field with long wavelength mediating modifications. Weinstein screening uses scalar field derivative interactions. Strong gravitational fields make nonlinear terms dominate, restoring GR behavior, while weak fields allow linear modification. Symmetron screening uses symmetry breaking dependent on density. High density maintains unbroken symmetry with massive scalar. Low density breaks symmetry with massless scalar. These mechanisms allow modified gravity models to satisfy tight solar system constraints while producing observable cosmological effects, but require specific field theory constructions that critics consider contrived. Testing screening requires measurements spanning density ranges from solar system to cosmic voids. Future tests of modified gravity include precision measurements of structure growth rate, how matter clustering amplitude evolves with redshift, which differs between GR plus dark energy and modified gravity, even if expansion histories match. Weak gravitational lensing and galaxy clustering combined measure both expansion through geometric distances and structure growth through clustering amplitudes, breaking degeneracies. The E-G statistic ratio of lensing to velocity perturbations tests GR directly by comparing two gravitational effects that should match in GR but can differ in modified gravity. Gravitational wave propagation speed, already tightly constrained, will improve further with future detections, ruling out additional classes of theories. CMB lensing, baryon acoustic oscillations, and redshift space distortions provide complementary constraints. Upcoming surveys DESI, Euclid, Roman, Rubin will measure these effects with sufficient precision to detect percent-level deviations from GR if they exist. Dark energy evolving equation of state. Dark energy's equation of state parameter W, defined as ratio of pressure to energy density W equals P divided by ρ, determines dark energy's gravitational effects and cosmic evolution. The cosmological constant has W equals -1, exactly negative pressure equal in magnitude to energy density producing repulsive gravity driving accelerated expansion. Observational constraints from type Ia, supernovae, baryon acoustic oscillations, cosmic microwave background, and weak lensing currently measure W equals -1.03 plus or minus 0.03, consistent with cosmological constant within uncertainties, but allowing modest deviations. If W differs from -1 or varies with time as WZs, dark energy is not cosmological constant, but dynamical field quintessence if W greater than -1, phantom energy if W less than -1. Measuring W precisely and testing whether it evolves constrains dark energy's physical nature, cosmological constant, scalar field, modified gravity, or something more exotic. The cosmological constant has W equals -1, exactly because it represents vacuum energy density constant in space and time. Vacuum energy density remains constant as space expands, creating energy from nothing. Allowed because negative pressure does negative work, exactly cancelling energy increase, making total energy conserved. The constant's attraction comes from theoretical simplicity and observational consistency. However, cosmological constant suffers profound theoretical problems. Quantum field theory predicts vacuum energy should be enormous, 10 to the 120th times observed value, the worst prediction in physics. Fine-tuning to cancel this enormous theoretical value down to tiny observed value seems unnatural. Additionally, cosmological constant provides no explanation for why dark energy density today approximately equals matter density, the coincidence problem. These theoretical issues motivate alternatives despite observational success. Quintessence models invoke slowly rolling scalar fields, analogous to Higgs field, but cosmologically important, whose potential energy density drives acceleration. Unlike cosmological constant with W equals -1 fixed, quintessence has time-varying equation of state T depending on fields' kinetic versus potential energy. When kinetic energy dominates, W approaches -1/3, producing deceleration. When potential energy dominates, W approaches -1, producing acceleration. The field rolls down its potential over cosmic time, causing W to evolve. Typical quintessence models have W greater than -1 always, remaining above cosmological constant. Observations constrain quintessence through WZ measurements at different redshifts, varying W leaves signatures in expansion history, measurable through supernova distances, BAO scales, and CMB acoustic peaks. Current data are consistent with constant W equals -1, but allow roughly 10% variation. Phantom energy describes hypothetical dark energy with W less than -1, producing pressure more negative than cosmological constant. Phantom energy violates all energy conditions requirements, that energy density and pressure satisfy certain inequalities to avoid pathologies like causality violation. Specifically, null energy condition requires ρ plus p greater than or equal to 0 violated when W less than -1. Phantom energy has bizarre properties. Energy density increases as universe expands rather than diluting, leading to big rip finite, time-future singularity where expansion rate diverges, tearing apart all bound structures. A universe dominated by phantom energy with W equals -1.5 would hit big rip in roughly 50 billion years, first unbinding galaxy clusters, then galaxies, then stellar systems, then atoms, then nuclei, as accelerating expansion overcomes progressively stronger binding forces. Most physicists consider phantom energy unphysical, but observations don't exclude W less than -1, leaving it an uncomfortable possibility. Redshift evolution WEDS is parameterized phenomenologically as WZ equals W0 plus WA times 1 minus A, where A equals 1 divided by 1 plus Z is scale factor, W0 is present-day value, and WA is evolution parameter. This linear parameterization captures first-order W variation with redshift, sufficient for current observational precision. If WA equals 0, dark energy is constant W fluid. If WA not equal 0, W evolves increasing, becoming less negative, weaker repulsion. If WA less than 0, or decreasing, more negative, stronger repulsion. If WA greater than 0. Future surveys aim to constrain WA to 0.05 precision, sufficient to distinguish between quintessence models with different potentials. More complex parameterizations include WA equals W0 plus WA times A plus WB times A squared for capturing nonlinear evolution, or bind WZ measuring independent W values in redshift intervals. Observational constraints on W and WA come from multiple probes measuring expansion history and structure growth at different redshifts. Type Ia supernovae at Z equals 0.01 to 1.5 constrain W0 through distance redshift relation deviating from matter-only cosmology. Baryon acoustic oscillations in galaxy clustering at Z equals 0.5 to 2.5 measure angular diameter distances, and Hubble parameter through BAO scale, constraining WED's evolution. CMB acoustic peaks measured by Planck constrain W through geometric projection. Dark energy affects last scattering surface angular diameter distance. Weak gravitational lensing measures matter clustering amplitude evolution, which depends on W through structure growth suppression. Stronger dark energy more strongly suppresses growth. Combining all probes, current best constraints are W0 equals minus 1.03 plus or minus 0.03 and WA equals minus 0.03 plus or minus 0. 3. Consistent with cosmological constant, W0 equals minus 1, WA equals 0. But uncertainties allow significant evolution. Current tensions, suggesting W may vary with redshift, come primarily from Hubble constant discrepancy. Early universe CMB infers lower H0 than late universe supernovae, potentially reconcilable if dark energy was weaker, less negative W, at early times, and stronger, more negative W, recently, changing expansion history. Early dark energy models propose additional dark energy component present before recombination that reduces sound horizon size, increasing CMB inferred H0 to match local measurements. These models require fine-tuned WZ evolution, W approximately minus 1/3 at recombination mimicking radiation, transitioning to W approximately minus 1 today. Other tensions include SATE parameter matter clustering amplitude, showing discrepancies between early time CMB and late time weak lensing measurements, potentially indicating W evolution affecting structure growth differently than constant cosmological constant predicts. However, these tensions might reflect systematics rather than genuine W evolution. Early dark energy models alleviate Hubble tension by modifying pre-recombination expansion, reducing sound horizon, the co-moving distance sound waves traveled before recombination which CMB acoustic peaks measure. Smaller sound horizon means CMB peaks at given angular scale correspond to smaller physical scale, requiring higher H0 to reconcile with peak positions. Early dark energy contributes 5 to 10% of total energy density around recombination, with equation of state W approximately minus 1/3, mimicking radiation's W equals 1 divided by 3 inches expansion equations, but with opposite sign. This increases expansion rate slightly at recombination, reducing age and sound horizon by few percent. raising CMB inferred H0 from 67 to 70 km per second per megaparsec, still below SH0. ES is 73, but reducing tension. The dark energy then dilutes as W transitions to -1, becoming negligible until recent epochs, when standard cosmological constant dominates. Early dark energy models face challenges matching all CMB features beyond acoustic peaks, particularly damping tail and lensing amplitude, cosmic strings, and topological defects. Phase transitions in the early universe, analogous to water freezing or magnetic materials becoming magnetized below critical temperature, occurred when the universe cooled through specific energy thresholds where symmetries of fundamental forces broke spontaneously. Grand unified theories predict that strong, weak, and electromagnetic forces, unified at temperatures exceeding 10 to the 15th Kelvin or energies above 10 to the 16th GV, separating as the universe cooled below this threshold during the first 10 to the -35th seconds. Electroweak symmetry breaking, separating electromagnetic and weak forces, occurred at 10 to the 15th Kelvin, around 10 to the -11th seconds. These phase transitions proceeded through bubble nucleation small regions, adopting the new broken symmetry phase, expanding and colliding with neighboring bubbles, where bubbles met with incompatible symmetry-breaking orientations. Topological defects formed stable or metastable configurations, where field cannot smoothly interpolate between different vacuum states, trapping energy in localized structures, persisting long after the phase transition completed. Topological defects come in 4 types, depending on dimensionality. Monopoles are point-like, zero-dimensional defects predicted when non-abelian gauge symmetries break. Domain walls are 2-dimensional, sheet-like defects, forming at boundaries between regions with discrete vacuum choices. Cosmic strings are 1-dimensional, line-like defects, forming where symmetry-breaking fields wind around in field space, and textures are unstable field configurations that form and decay but lack topological stability. Each defect type has distinct observational signatures and cosmological implications. Monopoles, if they formed in early universe, would overclose the universe. Their mass density would exceed critical density by enormous factors, constituting a major problem for grand unified theories, unless inflation diluted them to unobservable densities. Domain walls similarly overclose, unless the wall-forming transition is forbidden by additional symmetries. Cosmic strings and textures avoid overclosure, making them observationally viable defect candidates. Cosmic strings are 1-dimensional topological defects predicted by many grand unified theories and string theory-inspired models, where a complex scalar field winds around a closed loop in field space, trapping energy in a line-like configuration. The string's thickness is roughly the Compton wavelength of the field, typically 10 to the -30th centimeters for gut-scale symmetry breaking, making strings effectively 1-dimensional on cosmological scales. The string's tension, defined as energy per unit length, is typically 10 to the 6th Planck masses per Planck length, or approximately 10 to the 22nd grams per centimeter for gut string. This enormous tension means a string segment crossing our solar system would have mass roughly 10 to the 13th kilograms per meter, comparable to Earth's total mass concentrated in meter-long segment. Strings can be infinite stretching across the observable universe or form closed loops, ranging from microscopic to galactic scales. Networks of strings evolve through intercommutation, where crossing strings exchange partners, chopping loops off infinite strings and causing loops to fragment. Gravitational effects of cosmic strings include conical spacetime geometry around them. Spacetime is locally flat but has angular deficit, like removing a wedge from paper and gluing edges together. A particle circling a string completes circuit having traversed angle less than 360 degrees by deficit angle proportional to string tension. This creates gravitational lensing, where light passing on opposite sides of string produces double images of background sources separated by deficit angle, typically microarcseconds for gut strings. Unlike lensing by point masses producing curved distorted images, string lensing produces two undistorted images, characteristic signature allowing identification. Additionally, strings moving through space at relativistic velocities produce wakes, sheet-like overdensities of matter gravitationally attracted to the string then left behind as string passes, receding structure formation. These wakes would create distinctive patterns in galaxy distributions detectable through statistical analysis of large-scale structure. CMB signatures from cosmic strings include temperature discontinuities across string locations, step function temperature jumps as strings passing through last scattering surface create velocity discontinuities in photon baryon, plasma and B-mode polarization from vector perturbations induced by string wakes. Strings contribute to CMB power spectrum at all angular scales, producing excess power distinguishable from primordial fluctuations near scale invariant spectrum. The string contribution scales as square of string tension constrained by Planck satellite measurements to contribute less than roughly 1% of total CMB power at L equals 10, corresponding to string tension limit g mu less than 10 to the minus 7th, where g is Newton's constant and mu is energy per unit length. This rules out simplest gut-scale strings, but allows lighter strings from electroweak or intermediate-scale symmetry breaking. Searches for linear temperature discontinuities in Planck maps found several candidates, but none confirmed definitively as strings rather than chance alignments of primordial fluctuation. String networks evolve through complex dynamics involving three main processes: expansion stretching strings, intercommutation when strings cross-exchanging partners, and gravitational radiation from oscillating loops. Infinite strings stretch with cosmic expansion, maintaining roughly constant string length per Hubble volume. Each horizon-sized region contains several long strings on average. When strings cross, they intercommute with probability near unity, reconnecting and forming loops. These loops oscillate under tension, radiating gravitational waves and gradually losing energy, eventually decaying when size shrinks to Schwarzschild radius, becoming tiny black holes. The network reaches scaling solution where string density relative to total energy density remains constant over cosmic time. Creation of loops through intercommutation balances, loop decay through radiation, maintaining equilibrium. This scaling prevents strings from dominating energy density and overclosing universe, making them cosmologically viable, unlike monopoles and walls. Observational limits from CMB, pulsar timing, and gravitational wave observations constrain cosmic string parameters. Planck's CMB data limit string contribution to power spectrum, g mu less than 7 times 10 to the minus 7th from temperature data alone, tightening to g mu less than 2 times 10 to the minus 7th when combining temperature and polarization. Pulsar timing arrays, including nanograv, monitor millisecond pulsars arrival times with nanosecond precision, detecting correlated timing residuals from stochastic gravitational wave backgrounds. Cosmic string networks produce gravitational wave background from loop oscillations and decay, with spectrum depending on loop distribution and string tension. Nanograv's 2023 detection of gravitational wave background is consistent with supermassive black hole binaries, but allows possible string contribution up to 30%, corresponding to g mu approximately 10 to the minus 11th for optimistic loop models. Future pulsar timing with square kilometer array will improve sensitivity, definitively detecting or ruling out strings in parameter ranges 10 to the minus 12th, less than Gmu, less than 10 to the minus 7th. Cosmic strings could explain some CMB anomalies if they contributed to large-scale power through string segments present at recombination. The cold spot, axis of evil alignment, and hemispherical asymmetry might partially result from strings or string networks breaking statistical isotropy. However, current models struggle to reproduce. Observed anomaly pattern strings produce distinct signatures, like temperature discontinuities and specific polarization patterns not obviously matching anomalies. Additionally, Planck constraints limit string contributions to few percent of total power, making dominant string explanations unlikely. Strings might contribute subdominantly, adding to primordial fluctuations and creating rare large amplitude features when string segments happen to align favorably. But demonstrating this requires detailed modeling comparing string network simulations to data. Most cosmologists consider strings plausible contributors to CMB, but not primary anomaly explanations, without stronger theoretical motivation and observational evidence. Multiverse collision, eternal inflation. Eternal inflation, a generic prediction of many inflation models, proposes that while inflation ended in our observable universe 13.8 billion years ago, it continues eternally in most spatial regions, never ending globally. Inflation operates through quantum fluctuations of the inflaton field, the scalar field driving exponential expansion. In some regions, quantum fluctuations push inflaton up its potential, increasing field value and prolonging inflation. In other regions, fluctuations push inflaton down, ending inflation and allowing normal Big Bang expansion. Because space expands exponentially during inflation, regions still inflating grow faster than regions where inflation ended, ensuring inflation-dominated regions always occupy larger volume despite continuous inflation-ending transitions. Eternal inflation thus produces infinite space containing infinite bubble universes like ours, where inflation ended, separated by eternally inflating regions. Our observable universe represents one finite bubble nucleating from inflating background, constituting infinitesimal fraction of total space. Bubble universes nucleate through quantum tunneling inflaton field, quantum mechanically transitions from metastable false vacuum supporting inflation to true vacuum where inflation ends, creating expanding bubble of true vacuum. The bubble's interior expands normally following Friedmann equations, while exterior continues inflating exponentially. Bubble walls expand at nearly light speed, driven by vacuum energy difference between inside and outside. Different bubbles might have different low-energy physics particle masses, force, coupling strengths, cosmological constants if symmetry breaking during inflation ending produces different vacuum states. String theory predicts landscape of 10 to the 500th possible vacua, each corresponding to different effective field theory at low energies. Bubbles, sampling different vacua, would have radically different properties, most inhospitable to life. Anthropic principle suggests we necessarily observe bubble compatible with complexity and observers, explaining why our bubble has apparently fine-tuned properties. Bubble collisions occur when expanding bubbles' walls intersect, creating complex collision dynamics studied through numerical general relativity simulations. When bubbles collide, collision imprints temperature and curvature perturbations on both bubbles' interiors, potentially observable as cosmic microwave background anomalies if collision occurred early enough in our bubble's history that perturbations remain within our observable universe. The collision produces characteristic signature, circular temperature pattern on CMB with cold or hot disk at collision center, surrounded by ring of opposite temperature, with size and amplitude depending on collision energy, timing, and relative velocities. Simulations predict collisions occurring during our bubble's inflation or immediately after could produce 10-degree scale features comparable to observed anomalies. Multiple collisions from different directions would create multiple circular features overlapping in complex patterns. CMB signatures of bubble collisions include circular temperature and polarization patterns with specific properties distinguishing them from primordial Gaussian fluctuations. The temperature profile is approximately azimuthally symmetric around collision center, but with detailed structure depending on collision parameters, energy difference between vacua, relative collision velocity, and timing. Polarization shows characteristic patterns, E modes and B modes, correlated with temperature in specific ways differing from acoustic oscillations. Simulations generate template collision signatures for various parameters, compared to CMB data through matched filtering and Bayesian analysis. Searches in WMAP and Planck data looked for circular features statistically significant against background fluctuations, testing whether observed features match collision templates better than random chance. Laura Mersini-Houghton and colleagues predicted before WMAP launch that multiverse collisions would produce cold spot in southern hemisphere CMB and overall hemispherical asymmetry based on eternal inflation models with specific landscape properties. When WMAP data revealed the cold spot and hemispherical asymmetry, they claimed vindication. However, the prediction's specificity is debated. Did they predict precise cold spot location and amplitude or general existence of anomalies? Additionally, their model predicts multiple collision signatures, yet only cold spot arguably matches. Systematic searches by other groups for collision signatures found no statistically convincing evidence. The strongest Planck-based searches identified several circular feature candidates, but concluded none exceeded 3 sigma significance after accounting for look-elsewhere effect and trial factors from testing multiple templates. Searches for circular temperature patterns in Planck data employed sophisticated statistical methods, including matched filtering, cross-correlating CMB map with template collision signatures, and scanning over positions and parameters Bayesian model comparison, calculating posterior probabilities for collision versus no collision hypotheses, and machine learning classifiers trained on simulated collisions to identify features in real data. The most comprehensive searches tested hundreds of collision scenarios, varying collision energy, timing, and geometry, seeking any significant detection. Results found several marginal candidate circular features at 2 to 3 sigma significance, but none reached 5 sigma discovery threshold. Most candidates were consistent with statistical flukes from cosmic variance, searching many possible collision parameters and positions increases probability of finding apparent features by chance. The Planck collaboration's official analysis concluded no definitive collision evidence exists, though data don't definitively rule out collisions with subtle signatures. Eternal inflation's theoretical status is controversial despite being generic prediction of many inflation models. Proponents argue that most single-field slow-roll inflation models produce eternal inflation through quantum diffusion quantum fluctuations, causing inflaton value to random walk faster than classical rolling, ensuring some regions inflate eternally. Observations confirming inflation also indirectly support eternal inflation as natural consequence. Additionally, string theory's landscape predicts 10 to the 500th vacua, making multiverse of bubble universes inevitable. Critics contend eternal inflation phases measure problem-defining probabilities in infinite multiverse requires choosing measure for weighting infinitely many outcomes, with different measures yielding contradictory predictions. Additionally, eternal inflation may be unprovable. Other bubbles are forever beyond our horizon, making multiverse empirically inaccessible except through rare collisions. Some argue this makes eternal inflation metaphysics rather than physics, unfalsifiable speculation beyond science's scope. Anthropic principle in multiverse context suggests physical constants and conditions in our bubble are constrained by observer selection. We necessarily observe universe compatible with our existence. In multiverse, most bubbles have random vacuum properties, incompatible with structure formation, chemistry, or life. But among infinite bubbles, some by chance have appropriate properties, and observers like us can only exist in those rare bubbles. This provides potential explanation for apparent fine-tuning why cosmological constant is tiny but non-zero, why electron mass has specific value allowing chemistry, why nuclear forces permit stable atoms. Without multiverse, these values seem arbitrary or requiring explanation. With multiverse, anthropic selection explains them. Random values across bubbles, but observers only arise in fine-tuned ones. Critics argue anthropic reasoning lacks predictive power and represents giving up on finding physical explanations. Proponents counter its legitimate scientific reasoning. If multiverse is real physical consequence of fundamental theory, beyond the particle horizon, unobservable influences. The particle horizon at co-moving distance, 46.5 billion light-years radius, defines the boundary of our causally connected region, everything from which light or information could have reached us during the universe's 13.8 billion year history. Beyond this horizon lie regions causally disconnected from us. No signal from there has arrived here. No signal from here has reached there. The disconnection is fundamental, not merely observational challenge. Even waiting infinite time won't allow communication with regions currently beyond the particle horizon if dark energy persists, because dark energy's accelerating expansion eventually carries them across the event horizon, permanently severing causal contact. The particle horizon grows with time in non-accelerating universes as light from increasingly distant regions reaches us, but dark energy complicates this. While the particle horizon still grows, the event horizon at 16 billion light-years represents shrinking region with which we'll ever communicate, asymptotically approaching us as acceleration increases. Causally disconnected regions beyond our particle horizon cannot directly influence us through electromagnetic signals, gravitational waves, or any causal physical process propagating at or below light speed. Yet, they might indirectly influence observable universe through superhorizon modes, density fluctuations, with wavelengths exceeding horizon size, created before inflation, when all observable universe was causally connected in subatomic region. During inflation, quantum fluctuations stretch to scales exceeding horizon, becoming frozen as classical density perturbations. When horizon grew during radiation and matter domination, some modes re-entered horizon. We observe these as CMB fluctuations and large-scale structure. But the largest modes remain partially outside horizon wavelengths, exceeding 46.5 billion light-years, meaning we observe only portion of their oscillation. These modes affect observable universe's average density and curvature, measurably even though their sources lie beyond horizon. Pre-inflation fluctuations representing primordial inhomogeneities existing before inflation began could create preferred directions or large-scale gradients affecting our observable patch, despite extending far beyond horizon. Standard inflation assumes initial conditions were quantum vacuum fluctuations in nearly homogeneous state, producing nearly scale-invariant Gaussian fluctuations. But if inflation started from more complex initial conditions, perhaps remnants of pre-inflation evolution, or earlier contraction phase large-scale anisotropies, or gradients could exist on scales exceeding our horizon, observable as systematic trends across observable universe. The hemispherical asymmetry, axis of evil, and possibly dark flow could arise from superhorizon gradients or preferred directions imprinted pre-inflation. Testing this requires comparing observations to predictions from inflation models with different initial conditions, though distinguishing pre-inflation physics from post-inflation evolution is challenging. The horizon problem that inflation solves illustrates superhorizon influence's importance. The CMB shows uniform 2.725 Kelvin temperature across regions separated by more than 100 times horizon size at recombination. Causally disconnected regions that never exchanged information yet have identical temperatures, to 1 part in 100,000. Without inflation, this seems impossibly fine-tuned. Inflation solves it by proposing that all observable universe originated from tiny causally connected region, smaller than atom, underwent exponential expansion, stretching it to enormous size exceeding today's horizon, then ended inflation allowing normal expansion. This ensures uniformity. The entire observable universe was thermally equilibrated before inflation, explaining observed isotropy. But inflation simultaneously creates new superhorizon scales fluctuations stretched during inflation to wavelengths exceeding horizon, affecting our observable region's properties through partial oscillations despite extending beyond observable limits. Current beyond horizon regions contain more universe, possibly infinite space, with unknown properties, since they're observationally inaccessible. If the universe is infinite, as flat geometry suggests, infinitely many galaxies, stars, and planets exist beyond our horizon, forever unseeable. These regions might differ radically from our observable patch if superhorizon gradients exist, perhaps different average density, curvature, or even different low-energy physics from string landscape vacuum choices. Alternatively, they might be statistically identical. Cosmological principle, extended globally, predicts uniformity beyond horizon, though we can't verify this empirically. Inflation's predictions depend on this assumption. Treating observable universe as representative statistical sample of infinite whole allows calculating predicted fluctuation statistics. If beyond horizon universe differs dramatically, our observable patch might be atypical, biasing cosmological parameter inferences. Dark flow as evidence for beyond horizon structures represents one possibility if confirmed coherent 600 to 1000 km per second bulk motion towards Shapley region might result from massive supercluster or collection of superclusters beyond our horizon, gravitationally attracting local matter. If a 10 to the 17th or 10 to the 18th solar mass concentration exists beyond horizon in Shapley direction, its gravity could influence galaxies within our horizon, despite the mass itself being unobservable. Simulations show that superhorizon density perturbations, large-scale modes with wavelengths exceeding horizon, do produce bulk flows within subhorizon regions. The amplitude depends on superhorizon perturbation amplitude and geometry. Lambda CDM predicts superhorizon modes exist from inflation, but with amplitudes too small to explain 600 to 1000 km per second flows, unless combined with rare statistical fluctuations. Confirming this requires ruling out systematic errors in kinematic SZ measurements and demonstrating flows can't be explained by known structures within horizon. Massive structures beyond the observable universe exerting gravitational influence represent theoretically allowed scenario where matter distribution's large-scale gradient extends beyond horizon, creating net gravitational pull despite source being unobservable. Gravity propagates at light speed, so gravitational influences from beyond horizon can't reach us. However, pre-existing superhorizon density gradients created during inflation and present since universe's beginning produce gravitational potentials affecting observable regions' evolution. If our observable universe lies on gradient from underdense to overdense, extending over scales exceeding horizon. Matter within horizon experiences net force toward overdense direction. This creates bulk flow observable as dark flow or affects expansion rate, producing local Hubble constant different from global average. Testing this requires comparing local structure to cosmological predictions, searching for evidence of large-scale gradients in galaxy distributions, weak lensing, or CMB. Observational tests for superhorizon influences include searching for statistical anisotropy in CMB power spectrum, if superhorizon mode exists with preferred direction, fluctuation amplitude should vary across sky, peculiar velocity flows bulk motions of galaxy clusters indicating superhorizon gravitational influence, violations of cosmological principle on largest observable scale structures, or gradients approaching horizon size that don't average out, correlations between CMB anomalies, and large-scale structure suggesting common superhorizon origin. Current data show marginal evidence in hemispherical asymmetry, axis of evil, and possibly dark flow, but statistical significance remains 2 to 4 sigma, suggestive but not definitive. Future surveys with larger volumes and improved systematics will test whether apparent anomalies strengthen or dissolve with better data, determining if superhorizon physics affects observable universe, or if anomalies are statistical flukes and systematics. Future observations testing the edge. The Vera C. Rubin Observatory, formerly Large Synoptic Survey Telescope, located on Cerro Pachon in Chile, will conduct the legacy survey of space and time starting 2025, imaging entire southern sky every few nights to limiting magnitude 24.5 over 10 years. Rubin's 8.4-meter primary mirror and 3.2 gigapixel camera will photograph approximately 20 billion galaxies, measuring positions, brightnesses, colors, and shapes with exquisite precision. LSST's primary cosmological goals include mapping cosmic structure through weak gravitational lensing, measuring dark matter distribution, discovering 100,000 plus supernovae for dark energy constraints, identifying millions of strong lenses for time delay cosmography, and cataloging cosmic voids for dark energy tests. For edge-of-universe distortions, Rubin will measure void statistics, number density, and size distribution versus redshift constraining dark energy equation of state evolution. Large-scale structure power spectrum measured to unprecedented precision will test cosmological principle, search for excess power from strings or superhorizon modes, and constrain structure formation physics. Euclid, European Space Agency's dark energy mission, launched July 2023, conducts wide-field imaging and spectroscopic surveys from L2 orbit covering 15,000 square degrees, 1/3 of sky, measuring galaxy positions, shapes, and redshifts for 1.5 billion galaxies. Euclid's visible and near-infrared imaging measures galaxy shapes for weak lensing, while spectroscopy determines redshifts photometrically to Z, approximately 2, and spectroscopically for H-alpha emission galaxies. Primary science goals include constraining dark energy through baryon acoustic oscillations, weak lensing, and galaxy clustering, measuring modified gravity through E-G statistic, comparing lensing to velocities, and testing cosmological principle through large-scale structure homogeneity. For edge anomalies, Euclid will definitively test KBC void hypothesis by mapping galaxy distribution and weak lensing convergence to Z equals 2, confirming or refuting large-scale local underdensity. Euclid will also measure CMB lensing cross-correlations with galaxies, testing Planck's lensing amplitude discrepancy. The Nancy Grace Roman Space Telescope, NASA's Wide Field Infrared Observatory, planned for mid-2022 launch, features 2.4-meter mirror and 300-megapixel infrared camera covering 0.2, 8 square degrees per pointing, 100 times Hubble's field of view. Roman will conduct high-latitude wide-area survey covering 2,000 square degrees to unprecedented infrared depth, measuring photometric redshifts and shapes for billions of galaxies. Primary cosmological programs include supernova survey, discovering 10,000 plus type Ia supernovae to Z approximately 2 for dark energy constraints, weak lensing, measuring cosmic shear and matter distribution, and galaxy redshift survey through infrared grism spectroscopy. Roman's unique capabilities include microlensing survey, searching for exoplanets and isolated black holes, potentially detecting primordial black holes if they constitute dark matter. For edge physics, Roman's deep weak lensing will test modified gravity through tomographic shear measurements, measure large-scale structure growth rate versus redshift constraining dark energy evolution, and search for primordial non-Gaussianity signatures in galaxy clustering. The Dark Energy Spectroscopic Instrument, mounted on Mayall 4-meter telescope at Kitt Peak, Arizona, began 5-year survey in 2021, measuring redshifts for 35 million galaxies and quasars across 14,000 square degrees, 1/3 of sky. DESI uses 5,000 robotic fiber positioners, simultaneously observing galaxies across wide field, achieving unprecedented spectroscopic survey speed. Target galaxies span redshifts Z equals 0 to 3.5, including emission line galaxies, luminous red galaxies, and quasars. DESI's primary goal is measuring baryon acoustic oscillations standard ruler at 150 megaparsec scale across redshift, constraining dark energy density and equation of state evolution. For edge anomalies, DESI will definitively test large quasar groups, measuring 3D positions of millions of quasars tests, where the huge LQG and Hercules Corona Borealis Great Wall represent real coherent structures or projection effects. DESI will constrain dark flow through peculiar velocity measurements via redshift space distortions and test KBC void through tomographic galaxy density mapping. CMBS-4, Next Generation Cosmic Microwave Background Experiment, planned for late 2020 seconds, will deploy approximately 500,000 detectors at South Pole and Chile, observing at frequencies 30 to 300 GHz, achieving sensitivity 10 times better than Planck. CMBS-4 goals include measuring primordial gravitational waves through B-mode polarization, detecting light relic particles through effective neutrino species NF and neutrino mass through damping tail suppression, and measuring CMB lensing to sub% precision for dark energy constraints. For edge physics, CMBS-4 will search for cosmic string signatures in temperature and B-mode polarization with sensitivity Gmu less than 10 to the -9th, test multiverse collision hypotheses through improved searches for circular features, measure ISW effect from voids and superclusters cross-correlating with galaxy surveys, and constrain superhorizon modes through improved large-scale anomaly characterization. CMBS-4 polarization will definitively test whether axis of evil and hemispherical asymmetry extend to polarization or are temperature only, constraining physical origin. The Square Kilometre Array, International Radio Telescope project with Phase 1 construction ongoing in Australia and South Africa, will achieve collecting area approaching 1 square kilometre through thousands of individual antennas, operating at frequencies 50 MHz to 14 GHz. SKA's unprecedented sensitivity enables HI intensity mapping, measuring 21 cm emission from neutral hydrogen without resolving individual galaxies, tracing large-scale structure through cosmic web to high redshift. SKA will map billion cubic light-years covering redshifts Z equals 0 to 3, measuring baryon acoustic oscillations, and redshift space distortions for dark energy and modified gravity tests. For edge physics, SKA's pulsar timing array, detecting 1000 plus millisecond pulsars, will achieve nanohertz gravitational wave sensitivity, testing cosmic string and primordial black hole models. SKA will also detect cosmic magnetic fields through Faraday rotation and synchrotron emission, testing whether large-scale fields exist from primordial or astrophysical origins, potentially explaining some anomalies. JWST, already operating since 2022, continues deep field observations, discovering galaxies to Z greater than 15 cosmic dawn epoch, testing whether structure formation matches lambda CDM predictions or shows tensions requiring modified cosmology. Early JWST results found unexpectedly massive and luminous galaxies at Z greater than 10, challenging standard formation models predicting smaller galaxies at such early times. Continued observations will determine whether these represent measurement uncertainties, selection effects favoring rare massive systems, or genuine tension indicating faster structure growth than predicted, possibly from primordial non-Gaussianity, dark energy evolution, or modified gravity. JWST spectroscopy, measuring galaxy formation and reionization history, constrains early dark energy models proposed to resolve Hubble tension. Additionally, JWST observes high redshift supernovae and quasars extending Hubble diagram to Z approximately 3, testing dark energy evolution and searching for deviations from cosmological constant. These future missions collectively will resolve current anomalies and tensions, either confirming new physics or demonstrating they result from systematics and cosmic variance. The Hubble tension will be resolved through multiple independent H0 measurements: JWST supernovae, Deci-baryon acoustic oscillations, Roman weak lensing and supernovae, CMBS4 improved CMB constraints. If tensions persist across all methods, new physics, early dark energy, modified gravity, or beyond, becomes compelling. The KBC void will be definitively tested by Deci and Euclid mapping galaxy distribution and Euclid weak lensing measuring matter distribution. Large quasar groups will be confirmed or refuted by DESI-3D quasar mapping. CMB anomalies will be characterized to high precision by CMB-S4 polarization and lensing. Dark flow will be tested through DC peculiar velocities and kinematic SZ with future CMB experiments. Modified gravity will be constrained through Rubin, Euclid, and Roman weak lensing, measuring E, G, and structure growth. Within 5 to 10 years, edge-of-universe distortions will either emerge as confirmed new physics requiring fundamental paradigm shifts, or dissolve as statistical fluctuations and systematic errors, settling current cosmological debates. Implications for cosmology and reality. The lambda CDM standard model achieves approximately 95% success, explaining cosmic observations. CMB power spectrum matched to sub% precision across 1,000 plus data points. Large-scale structure growth, consistent with predictions from initial fluctuations to present. Supernova luminosity distances tracing accelerating expansion. Baryon acoustic oscillations measuring geometric distances. Big Bang nucleosynthesis producing observed light element abundances, and galaxy formation qualitatively matching simulations. This extraordinary success makes lambda CDM the best-tested cosmological model in history, superior to any alternative by wide margin. Yet, roughly 5% of observations show tensions, Hubble constant disagreement, SATE, clustering amplitude discrepancies, CMB anomalies like cold spot and axis of evil, lensing amplitude being low, possibly dark flow. These tensions individually have 2 to 5 sigma significance, statistically significant but not overwhelming. but collectively suggest lambda CDM may be incomplete approximation to more complex reality. Anomalies and tensions include the Hubble tension at 5 sigma Planck cmb, inferring H0 equals 67.4, while SH0 ES supernovae, measuring 73 km per second per megaparsec, statistically incompatible discrepancy. CMB dipoles, including kinematic dipole from Earth's motion and potential large-scale anisotropies like hemispherical asymmetry, showing 7% power difference and axis of evil alignment, marginally consistent with chance, but collectively unusual. Lensing amplitude consistently low across Planck CMB lensing and galaxy weak lensing surveys, yielding SATE approximately 0.76 to 0.8 versus Planck primary CMB's 0.83, 2 to 3 sigma tension, indicating less structure than predicted. SATE tension also appears between different lensing surveys and between lensing and cluster counts, suggesting systematic issues or genuine physics. Additionally, large structures like Sloan Great Wall and potentially KBC void approach or exceed predicted maximum sizes, and possible dark flow indicates unexpected large-scale motions, though confirmation is lacking. Possible resolutions divide into systematics or new physics. Systematics explanations invoke unidentified measurement errors, calibration biases, foreground residuals, or analysis mistakes, producing apparent tensions without genuine physical discrepancies. For Hubble tension, systematic possibilities include Cepheid metallicity dependence, affecting distance ladder, supernova evolution with redshift, extinction corrections, or parallax zero-point errors. For lensing, shear calibration biases, intrinsic alignments, photometric redshift errors, or baryonic feedback could reconcile measurements. For CMB anomalies, residual foreground contamination, instrumental systematics, or look elsewhere effects from testing multiple hypotheses might explain features. Systematics are conservative explanations requiring no new physics, but extensive investigation has failed to identify specific errors large enough to resolve all tensions, making systematics-only explanations increasingly strained. New physics options include modified gravity theories like FR gravity, massive gravity, or other extensions to general relativity affecting structure growth, lensing, and expansion differently than lambda CDM. Early dark energy, additional component significant before recombination, reduces sound horizon and increases CMB inferred H0, alleviating Hubble tension but faces challenges matching other CMB features. Evolving dark energy with equation of state WEDS, varying from -1, changes expansion history and structure growth, potentially reconciling early versus late universe measurements. Extra-relativistic species like sterile neutrinos or other light particles affect expansion rate at early times, modifying CMB and BBN predictions. Massive neutrinos with total mass 0.2 to 0.3 electron volts suppress structure on small scales, reducing SATE and potentially explaining lensing tensions. Extra dimensions or modifications to gravitational force law at cosmological scales could explain acceleration without dark energy. Each proposal must satisfy all observational constraints, not just resolve one tension, making simple solutions elusive. Anthropic considerations raise the possibility that some apparent fine-tunings or coincidences reflect observer selection bias rather than physical explanations. If multiverse exists with varying physical constants, we necessarily observe bubble with properties compatible with complex chemistry and life, regardless of how improbable such properties are globally. This potentially explains cosmological constants' tiny but non-zero value. In most bubbles, it's zero or enormous, but observers require it to be approximately 10 to the -120th Planck density for structure formation to succeed without rapid Big Rip or collapse. Similarly, Higgs mass, quark masses, and other parameters might be anthropically selected. However, anthropic reasoning lacks predictive power. It explains why parameters have life-compatible values, but doesn't predict specific values within allowed range. Additionally, it's unclear which parameters are environmentally variable across multiverse versus fixed by fundamental theory. Using anthropics requires caution to avoid explaining away everything with selection effects, rather than seeking physical mechanisms. Limits of observation create fundamental unknowns about reality beyond horizons. The particle horizon, at 46.5 billion light-years bounds, the observable universe regions beyond, are causally disconnected and observationally inaccessible. We cannot know whether space is finite or infinite, whether cosmological principle holds beyond horizon, whether other regions have different physics, or whether beyond horizon structures influence us through superhorizon modes. The event horizon at 16 billion light-years represents future observability limit regions beyond will never be observable even given infinite time, as dark energy acceleration carries them away superluminally. Information loss occurs as structures cross event horizon, permanently lost to observation. We're fundamentally limited to studying our 9.3 billion light-year observable bubble, with everything beyond remaining speculative inference from theoretical extrapolation and hope that observable patch is representative. Future precision cosmology from Rubin, Euclid, Roman, DESI, CMBS4, SKA, and JWST will either reveal cracks in lambda CDM requiring new physics, or confirm the model with unprecedented precision, resolving tensions as systematics. If Hubble tension persists across all independent measurements, new physics becomes unavoidable, most likely early dark energy or modified expansion history. If SATE tension persists, massive neutrinos, modified gravity, or other structure formation physics is required. If CMB anomalies strengthen statistically and extend to polarization, primordial physics beyond simple inflation non-Gaussianity, cosmic strings, textures, superhorizon modes becomes compelling. If large structures like KBC void are confirmed, cosmological principle on largest scales faces revision. Alternatively, all tensions might dissolve with better data and systematics control, vindicating lambda CDM as complete effective theory, valid across all accessible scales. The next decade of observations will decisively determine cosmology's path forward. The ultimate question is whether the universe's edge, our observational horizons, and the anomalies observed there, reveals fundamental new physics, or represents statistical flukes, systematics, and cosmic variance within standard paradigm. Current evidence leans toward lambda CDM with percent-level modifications, no revolutionary overhaul needed, just refinements, but persistent tensions keep open the possibility of genuine surprises. If multiverse is real and superhorizon modes affect us, the edge's distortions might reflect beyond horizon influences we can never directly observe, fundamentally limiting cosmological knowledge. If cosmic strings, textures, or other topological defects exist, they represent relics from physics beyond standard model, providing windows to grand unification and early universe phase transitions. If modified gravity operates on cosmological scales, Einstein's theory requires extension to deeper framework, perhaps emergent gravity, entropic gravity, or other radical reconceptualizations. Whatever the resolution, studying the edge pushes observational cosmology to its limits, testing whether universe truly is comprehensible within physics, accessible from our finite observable bubble, or whether fundamental aspects remain forever beyond reach. Distorted by horizon effects, we glimpse but cannot fully understand. The edge may yet reveal reality's deepest secrets.